Okay, so good morning to everybody. We start the second day of our workshop with Kostas Skenderis on scattering amplitudes from holography.
Okay, thank you very much. First of all, thank you for organizing this very nice event. I entirely enjoyed yesterday, and I hope the next 2 days will be equally good. And I also want to encourage interactions. I want to reciprocate all the questions I've done yesterday. um, okay, so what I will discuss, actually a very nice introduction to the talk, was the last talk from yesterday. So let me give you first the very quick motivation. We all know that scattering amplitudes is one of the main quantum field theory observables. They provide the link between theory and experiment. And as physicists, we have to think not only about theory, but also how to connect with reality and how to connect with experiment. And the computation of scattering amplitudes is kind of standard part of textbook quantum field theory 101. And yesterday the last talk discussed some kind of new ways to approach the problem using ideas from N equals 4 Young Mills and so on. Today I'm going to suggest kind of a drastically new perspective, a new way of computing scattering amplitudes, not by staying in the dimension you are. Let's say we are in 4 dimensions. We may be interested in QCD or in LHC physics like yesterday, but this talk is about computing it by looking in conformal field theory in 1 dimension less. So again, if suppose you're interested in QCD, we'll be looking at a 3-dimensional conformal field theory. And then all of this talk is about explaining this bottom part of this slide. So what I will argue is you can take a limit of correlation function of a conformal field theory, and I will explain all of these things as we move on, where the entries are primary operators and the deltas are scaling dimensions. And this would compute a scattering amplitude in Minkowski space in 1 dimension higher. So again, the purpose of this talk is to explain which scattering amplitudes and what theory such a limit computes, and most importantly, what do I really mean by saying limit? Okay? At this point, you're not meant to understood this, but you're meant to be surprised. If you're interested in 4-dimensional physics, like QCD or LHC collider physics, why would you start looking at 3-dimensional conformal field theory? So who ordered that? And I think my title already, in a sense, gave it up. So this relation originates from holography. So holography relates d plus 1-dimensional quantum gravity with d-dimensional quantum field theory with no gravity in 1 dimension less. And the general expectation is that it holds for any gravitational theory. The idea originates from black hole physics. And as long as you have black holes, you should have holography. And in particular, it should apply to asymptotically flat gravity. And in asymptotically flat gravity, the observables are scattering amplitudes. And holography, this idea, suggests that they should have a description in some other quantum theory in 1 dimension less. So that's where the idea comes from. So actually, this is part of a kind of a Bücher cycle of ideas. So we have learned through the years that conformal field theory describes its kind of universality classes. So if you lock Go in the infrared, then you describe universal behavior of systems along distances. But this type of ideas puts CFT even in a more central role. So over the last 30 years, we learned that the CFT can be used to describe quantum gravity in a space with negative curvature. And what I will argue today is the CFT can also describe flat space scattering amplitudes. And I'm sure people might have seen me giving talks also about this arrow here. I think it's going to be a talk today later by Panos. how to kind of connect CFT with kind of cosmology. So this suggests a kind of a more central role for a CFT. And perhaps if there is the one thing you should remember from this talk, if you're not interested on ADS or scattering amplitudes, is this kind of bigger diagram. I think it's a kind of a bigger change and kind of moving towards a bigger kind of paradigm change. Okay, so of course the holography we understand mostly in the context of ADS CFT, as I said, and the idea that you can have flat space holography. Of course, even back in 97, 98, when ADS CFT started, the focus, or the community, did not just want to understand gravity with negative cosmological constant. People wanted to understand, in a sense, the flat space holography. And the idea of holography came from thinking about black holes in asymptotically flat space. So it was a very natural question to ask, how do you kind of generalize this duality to something that would apply to flat space? And surely, shortly afterwards, I mean, within a couple of years, two prominent members of the community came up with a suggestion, which makes complete sense. They say if you focus in a small neighborhood of a space-time, that should be insensitive to what boundary conditions you impose a few light years away. And therefore, you should be able to start from what you have here and then formulate a way to extract physics for flat space. Okay, this was 25 years ago. And I think it's fair to say there's a lot of work was done, and I will mention some in the next slide. But because this limit was so subtle, I don't think that question was considered either solved or solvable. So this work, it's the first of many papers to follow up, aims to provide a complete understanding of this limit. And I would claim we already have the complete understanding. We don't have all the details for all cases. As you will see, we will see at the very end how far we've gone and what we can say. But we do have a complete understanding of what is this limit. So most of the talk here would be about walk you through to understand the limit one needs to take. And it is a subtle limit. It involves many different things happening at the same time. And if you do not have them happening, all of them at the same time, you will find that the limit doesn't exist. And this is what people have found in the past. Okay, so this is based on a paper that appeared last summer. This one here. And as I said, this topic has a very long history, and I give here a very small list of people that contributed. It was mostly done, let's say there's more work roughly over the last 10 to 15 years, and it was not done in the context I'm discussing here, kind of top-down, but rather in a bottom-up type approach, or you try to sort of guess how the dictionary would work out, and then try to come up with a prescription and then test it. And there are, roughly speaking, two approaches. One goes under the work celestial holography, and this means that if you're interested in kind of the physics of flat space, you look at the celestial sphere, and you formulate the theory there. And then you try to formulate rules such that you would extract the physics of scattering amplitudes. And the second approach goes under the name Corollian holography, and roughly speaking, so this is a kind of codimension 2 holography. So you're looking at the celestial sphere, so it's 2-dimensional less. So it will be a 2-dimensional CFT from that perspective. Where the Corollian one is kind of more conventional holography. You say you're looking at stuff at the null infinity, and then you try to formulate a theory there. Because null infinity is a null surface that has very peculiar properties. I don't think it's, I mean, there has been a lot of work, so some of them by the people listed there, try to understand or make sense of what a Corollian quantum field theory is. I don't think this has been settled. So here we're gonna forget, at least for now, this bottom-up approaches and start from the top, kind of a duality we understand, and try to formulate the rules of the game starting from there. Okay, so that's my introduction. Any quick questions? Yes? yeah, so so these other approaches, they do not start from ADS, or some of them they do. But then as you zoom in, so I mean, ADS has a conformal boundary. So you zoom in a small region, and then as you zoom in, that in a sense develops its own asymptotics, which are the conformal boundaries where people think the dual theory is. It's not. I mean, in my case, you will see. You will see. In a sense, there are lots of red herring because many different people try to make sense of that limit, and they were making different guessworks, and sometimes using different the wrong kinematical variables, and then they couldn't make sense of it, so they were guessing some and then working some. There is a lot of good work, but there's also a lot of guesswork which needs to be, in a sense, weeded out. Now that we understand kind of a top-down, so I'm not going to, in a sense, do any of those. In a sense, this is part of my to do things. Now that one understands the top-down, go back and try to understand them. There have also been works where people try to connect them, and now there is quite a bit of literature that they show that there is a sense in which they're not really different, these two approaches. But now we're going to have a kind of a top-down. So what I will do today is first I will walk you through to define what this flat space limit is. Then after we define the limit, I will tell you what is the dictionary, how to go from 3 dimensions to 4. And then we'll discuss the simplest possible example, which is yet non-trivial and also has interesting physics. I will tell you how to compute electromagnetic form factors for 4-dimensional theories from CFT3. And then we'll very briefly flash the general case, and then I will conclude. Okay, so let's start from the beginning. So which theories? Is this for some specific special cases of theories, or is this general? So then I would claim that this can be formulated for any theory. So suppose you're interested in scattering amplitudes of some quantum field theory. So this will have some field content. Will have some the field content will have some particles that have some masses, and there will be some couplings. So this can be any model. Could be QCD, could be the full standard model, part of it, could be electroweak, could be beyond the standard model. You name it. Okay. This is our starting point. You tell me I want that theory, and then you give me that Lagrangian. And now my task is now to tell you how to go about doing the computation for this specific theory by studying some 3-dimensional quantum field theory. And the construction is as follows. The first step is to couple your favorite theory to ADS. So you put gravity and you put cosmological constant. Now ADS, so I'm going to work with this kind of Poincaré type coordinates in ADS, where this L is the ADS radius, which is related to the cosmological constant via this relation. And throughout this talk, I will also work with Euclidean ADS and Euclidean space. You can always weak rotate. So this weak rotation plays no role, can always be done at all steps in the computations I will describe. So we are interested not in the theory in ADS. So eventually we want to take the limit where the cosmological constant disappears. And taking L lambda to 0 means taking L to infinity, the ADS radius to infinity. So that's one element of the limit. This is something that everyone was said in the past. But L is a dimensional parameter. So when we take the limit, we have to specify which dimensionless combinations are kept fixed. Yes?
When you do this, you also change, of course, the metric appearing inside there.
Yeah, absolutely, absolutely.
It was the same method
Yes,
before,
yes.
But it's not really the same method before. The metric
It is, yeah. So in a sense, the couplings here that were before with the flat kind of contractions with flat metric now become contractions with the ADS metric. Absolutely.
But you do not react on ADS. So the space is ADS, and those fields do not change the geometry.
No. For the purpose of scattering amplitudes, I'm not going to back react. I'm going to do it in fixed ADS. If you want to do, let's say, include gravitational scattering, I will perturb around ADS. So the only thing that matters is that asymptotically, the space becomes asymptotically locally ADS, like the standard way it says we do holography.
Why do we need gravity? In fact, this limit we can take it without with non-dynamic method.
Yeah, so here I'm trying to formulate it in the biggest possible, in a sense, setup. And also for holography, I really need also to have gravity. But I can decouple gravity. That's why well, I didn't emphasize it here. So here, this can be with or without dynamical gravity. So if I want, and as I will state today, most of it without gravity, then you can also, in addition to taking that limit, you also need to scale, g to infinity so that you kind of freeze out gravity. Yes?
How about the vacuum of the theory? Suppose you go to the vacuum of Minkowski, right?
Yes, so the vacuum,
Is that unique?
in this, the interesting non-perturbative questions, which I'm not going to touch. As I said, this is the first of many papers to appear, hopefully by other people in the audience as well. So, so here I'm just going to formulate the question of scattering amplitudes in kind of standard Minkowski vacuum. Then you can go on and ask other questions.
But you're supposed to start from ADS, right?
I'm starting ADS.
So you're supposed to give some vacuum? Or is that unique?
So in ADS, I'm going to start with the standard, in ADS, the vacuum is unique, kind of the usual CFT on a ground state. I mean, you will see, in a sense, the fact that you're right to ask about the nature of the limit, because again, the last 25 years, there were continuous papers that had different issues coming up. In this case, it will be constructive. So by the end, I finished the talk, you will see, in a sense, what elements I need. Now, if you try to extend it before the things we have explicitly demonstrated the existence of the limit, there may be additional issues. There may be also a question, does this theory, the one that I really want to end up, really exist? That's also, that touches upon issues of the swampland that we heard yesterday in a number of talks. Yeah, so within, in a sense, within the regime where I do the scattering amplitudes, all of this is fine, and all of this have been checked. It's just to all orders, as you will see at the end. But all of this are definitely relevant questions, because again, throughout this 25 years, there was a lot of confusion. And now we start, in a sense, to see the light at the end of the tunnel, because we really understand all the elements you need to do. And then you can go to different directions and ask questions like this one. Yes? You mean the kind of the soft theorems and so on? That's another interesting question. I am working on this. Yeah, I think it's all part in there.
Perhaps some of these questions will be answered along the way.
Yes. Yeah. Otherwise, we're not going to finish. Yes. Yes. So first, how to go? Let's do first the simple baby steps first, kind of from ADS to flat space. So if you start from this metric here and reparameterize the radial coordinate in the way I indicate over here, and then, sorry, this should have been infinity, and L to infinity, this metric here becomes Euclidean space. And you can see time, of course, this, upon further wake rotation, this becomes the usual time in Minkowski space. So time emerges from the radial coordinate. And then one can also check that you can start from the isometries of ADS, and this limit, this exactly become the isometries of flat space. And if you want to get a little bit of intuition about how the isometries emerge, recall that in ADS, the ADS isometries is the same thing as a conformal group in the dimensions, and then the boost and time translations. So here, once you're in flat space, you can do time translations, and you can also have kind of boosts that mix the two. All this emerge from dilatations and spatial conformal transformations. Okay, now to tell you how the limit works, I have to tell you a couple of things about ADS CFT. So in ADS CFT, we get a relation between ADS observables and CFT observables. And roughly speaking, it works like this. So Euclidean ADS, you can think as a ball, where the boundary is this blue circle and the interior is here. And now the CFT lives at the boundary of the space. And in these coordinates, where it lives is it lives in this part and has this length scale, L, appearing in front of it. So here we learn the first element of the kind of the dictionary. So you want to take L to infinity. This means that we need to focus on the deep infrared of the CFT. And this also means you need to focus in the deep interior of ADS. So you kind of recover the intuitive idea that Burczynski and Susskind had in the...
CFT is on the sphere, right?
The CFT is not on the sphere, it's on flat space.
Only if you take the limit. Before it's on the sphere.
Before that, it's, okay, it is in the Einstein universe, in the Minkowski space, or it is on... I mean, you have ADS have a conformal boundary, and then I can choose, well, the metric, I can choose the flat metric on the conformal boundary, and then work with the flat metric. So as long as I impose the right boundary conditions at the additional point, convectifies Minkowski to the sphere, then the physics is the same. Yeah, so I will be working with the boundary conditions where I chose the right boundary conditions, so it's the theory on flat space. Okay. Now I need to tell you a couple of things about CFT. I'm not assuming everybody knows, or at least give you so that we're on the same page, the definitions. So CFT consists of a set of operators. Yeah. So that's, this is, from here we go from ADS in D+1 to Minkowski in D+1. And then I will discuss things in terms of CFT in D dimensions.
Right, okay.
Yes.
So we're still in D+1.
In D+1, yes. So the CFT is in one dimension less. ADS and Minkowski are in the same dimension. Yes. Okay, so so the CFT has a set of operators that have a scaling dimension. For example, such operators are the energy momentum tensor and symmetry currents that will also appear later on. And then a way to multiply these operators quantum mechanically. So this is called operator product expansion coefficients. And if you have the spectrum and the OPE coefficients, in principle, this gives you a unique way to obtain all observables, which are all correlators, kind of endpoint functions of these objects. Now, what ADS-CFT does is tells you a way to compute the same object by doing a gravitational computation. Okay. Now, again, I need to review a couple of things about how the dictionary works in ADS. So the masses in the bulk of ADS and the dimensions in the boundary theory are related by relations of this form. So this is for scalar fields, but there's similar relations for all cases. So delta in CFT maps to an M in ADS. And the OPE coefficients are related to the bulk couplings, the couplings that appear in the Lagrangian of the CFT. So now, so we have these relations. Now we need to take the limit L go to infinity. So from here, we see there are two cases. So if the mass is non-zero, so the second case, suppose you want to have the Higgs boson in your theory, so I have to have non-zero mass. Then this means that as I go L to infinity, in order for this to remain finite, delta has to scale to infinity in a rate which is fixed. So I have to be kind of linear trajectories in a space of dimensions where the slope of the trajectory is related to the mass of the particles you want to keep. On the other hand, if you have deltas which are of order 1, small delta, the low-lying spectrum of the CFT, all of this are going to map to massless case after the limit. Secondly, we want to keep, as I said, we want to keep the back couplings fixed as we take the limit. This means that all OP coefficients should be kept fixed in the limit.
Sorry, Pastor. Does that mean that in order to do this, one of the theory has to be massless?
No, my quantum theory would be, I will discuss a massive example. I have to have the dimensions. We have to go, the spectrum of the theory should have a series of operators.
I'm talking about the MI, because the MI are where you start from. Somebody gives you a theory and it has some mass.
Yeah, exactly. So suppose you gave me the standard model that has massive quarks and the Higgs and all of that. So this means the CFT, I will have to look at the spectrum of the CFT, and there should exist such a CFT, which is a non-trivial question as I will move on. I will look at the operators of the CFT that have the same quantum numbers, but deltas scale to infinity.
Dimensionless and everything is dimensionless, so I don't understand.
Well, you do it in Planck units, the natural units of your theory. I mean, the theory is not scale invariant.
Which theory? The gravitational theory? The gravitational theory is not.
We're living today in this universe that has a standard model, and there are standard units, right? Kind of. You can choose these units to be, normalize them kind of Planck units, whatever units you choose to normalize your theory. So this relation here is in these units that of the theory you're interested in.
That you say that you declare this to be the natural unit of your theory.
Yes, yeah. Okay, so now let me summarize. So what I told you is the flat space limit from the perspective of the CFT is the following. You need to focus on the deep interior of the CFT. If we have massive fields, the CFT should contain operators of dimension delta that scales to infinity with a slope which is related to the mass. The OPS coefficient should be kept fixed, and there is an additional requirement that will only become apparent towards the end of the talk. We also need to renormalize these operators, and the renormalization is either infinite or zero, depending on whether the dimensions are of order 1, these correspond to massless fields, or the dimensions go to infinity, and there are specific formulas about this. It's not just how it behaves. There is a very specific way with which you need to renormalize the operators. And you need to do all 4 at the same time. So there are papers where they do some of this, but not all. And unless you do all 4, the limit doesn't exist. Yes?
So maybe it's nice that, okay, this link dimension, when you calculate the 2-point function, for example, this link dimension is the exponent of the distance on the denominator.
Yes.
If this goes to infinity, it's like, does it mean that it doesn't propagate, or what?
Well, let's wait to see a bit more how it works in practice, and then. Okay, so this is the limit. So now I want to tell you about the dictionary. So if you're interested in scattering amplitudes, okay, this depend on shell momenta in d+1 dimensions, namely momenta that square to the mass of the particle that's scattered, and polarization vectors. And the scattering amplitudes in flat space, they're proportional to a momentum, an energy momentum preserving delta function times the reduced amplitude. And many of the difficulties, if not all of the difficulties that people had in the past, was because of this momentum preserving function. Because since the amplitude is 0 everywhere except at the locus of the 0 of the delta function. And unless you have the right kinematical variables, you're not going to land in that locus of the 0 of the delta function. Okay, so then you need the right kinematics. Okay, what are the kinematics? So it's d-dimensional CFT. Now we need to map the d-dimensional variables appropriate for a CFT to the variables of the scattering amplitudes. So this is about this slide here. So because I want to make this problem as easy as possible, I will work on a CFT in momentum space. Usually CFT is worked out in position space. But over the last 10 years or so, I have worked quite a bit developing how to work out the CFT in momentum space. So if you work in momentum space, so then the CFT, the endpoint function of a CFT is determined by, so you need to give momenta, off-shell momenta. And then because you have translation and invariance, you automatically have a momentum preserving delta function. And now the d+1 dimensional momenta, the momenta that the scattering amplitudes depend on, are given via this very simple and intuitive formula. So the momenta of the CFT becomes special momenta in one dimension higher. And the zeroth component, the energy variable, is just the usual on-shell condition with plus minus depending on whether your particles are going to be incoming or outgoing. Okay, so now I gave you a map. And now the claim is that now if you use this identification and you take the limit out to infinity, the one I just described, this will give you this scattering amplitude. So with this kinematical identification, part of this delta function, part of this delta function is trivial, namely the spatial momenta, because it's already here. So the non-trivial part is to show that this energy-preserving delta function emerges in the limit. And it does. They also emerge in the limit. I will come back to that in a few slides. So instead of telling you the general case, which I will just kind of flash at the very end, I'm going to now discuss this in a simpler setup, that of electromagnetic form factors. How much time do we have? Just to see what I need. Yeah, should be fine. Okay. So let's discuss briefly electromagnetic form factors. What are they first? Well, electromagnetic form factors are expectation values of the electromagnetic current in single particle states that carry momentum and spin s. So these are some of the most basic observables. So for instance here, this is the Penrose diagram of Minkowski. So if you have massive particles, they originate from sky minus, they go to sky plus, and these are null infinity, so radiation comes from here and observed over there. Suppose you generate an excited state that emits some light, which you observe, and then the particle, and then you have the particle that decays. By just looking at electromagnetic radiation there, then you can infer the couplings of the photon to the corresponding massive field. And that's how people were finding these couplings back in the 50s. They were just generating excited state. They're even doing now. You have excited hadronic states, and then you either scatter light, or if it is excited state, you see the light which is emitted. Then you decompose it in multiples, and then from the multiples you extract the couplings. So for example, if you have a spin S state, there's a general result that this has 2s plus 1 electromagnetic form factors. So a famous case, which is instrumental in the development of quantum mechanics, was for the spin half particles like the electrons, where now you have two couplings. One corresponds to the charge, and the other is the magnetic dipole. And this essentially determines the gyromagnetic ratio. If you have a massive spin 1 field, like the W boson, then you have 3 electromagnetic couplings. One is the charge, the magnetic dipole, and the electric quadrupole moment. And again, this was the main game in town in the 50s, where people start having big enough accelerators to generate excited states, and then we try to determine what is the physics of them.
Particles are massive. If they are massless, does this still hold?
Yeah, you can still have, well, yes, you can still have, yes, yeah, even with massless. Because then it's going to be a different diagram than this, right? It's going to kind of start from here and then scatter out there. And this is still an active field. For instance, the determination of form factors for hadronic states is still an active field of research, and one of the biggest theoretical uncertainties in the determination of the mu and G-2 factor, which has been over the news a couple of times over the last couple of years, is due to uncertainties in the form factors. So potentially, and I'm not saying I'm doing this, but potentially these new methods could give you a new non-perturbative way to attack this problem, and not just using lattice QCD, which lattice methods, which is people are currently using. Okay, so now what I want to do is I want to tell you how I want to demonstrate how to compute the massive speed 1 electromagnetic form factor from conformal field theory. So I have reviewed for you the dictionary. So let's apply it for in the case at hand. So the photon corresponds to a conserved current, and we have a massive vector boson. So this corresponds to a non-conserved vector operator. So if I want to know the form factor, then I need to compute this 3-point function of the CFT. So I have two non-conserved vectors and one conserved current, and I need to take the limit L to infinity, as I described earlier, and that should give me this energy momentum preserving delta function times the scattering amplitude, including polarization vectors and everything. Okay, now to tell you how to do this limit, I first have to tell you a little bit how to compute this object in momentum space. So that's something, again, I developed over the last 10 years or so. So the first step in that program is to use the fact that the momenta provide you kind of a linear space that you can express all tensorial properties. So the tensorial properties are the fact that this has 3 indices. It's carried out by tensors, which are constructed from momenta and the metric. And this is something you need to do at every, in each case. So for this specific correlator, this is something we've done in a previous paper by the same authors. And there are 6 such tensors. It's not so hard to actually write them down. And then the CFT correlator is given by these tensors and then multiply by general form factor that depend on the magnitudes of the momenta P1, P2, and P3. Now, conformal invariance, now you impose conformal invariance on this object, and this implies that these form factors satisfy specific differential equations, which you can solve in complete generality. And now, after the dust settles, this correlator here is determined up to 3 constants. Okay? And these form factors here are given as in terms of a so-called triple K integrals of this form. So I have an integral that involves 3 Bessel functions, these modified Bessel functions. And these integrals depend on 4 numbers, alpha, beta 1, beta 2, and beta 3. I mean, these indices of these numbers, and these are essentially determined by the dimension of the dual operator. Okay, so if you're giving dimensions, then you get this i's, and then the correlator is given in terms of these objects. Now, in this limit, this integral is like an integral over energies, and then this upper limit is the infrared of the theory, when the lower limit is the UV of the theory. So over the last 10 years, I have been mostly focusing on this part here to understand renormalization. But for this talk, I'm going to focus on the other limit up there. And to focus on that limit, while keeping the kinematics were interesting valid, we're going to change variables in this integral by doing this change of variables. So if you have a good memory, you've seen this formula before. This was the formula when I went from ADS to Minkowski. So we change these variables, take L to infinity while keeping fixed the momenta and this ratio, right? Because this is part of taking the limit. And when you take this limit, it turns out all of these integrals become proportional to an energy preserving delta function. That's how this energy preserving delta function emerges, times a factor, which is either infinity or 0, and it's precisely this factors I told you in here. And then one can show in generality that you can always remove these factors by doing the normalization of the operators, not just for this case, in generality. So now,
X is just simply in the equation variable. It is not. It's morally like spatial coordinate, but
yeah. So from this perspective, it's just an integration variable. So here I'm just telling you how to focus in the regime of interest, which is the infrared. And then in maybe 2 slides, I'll connect this back to kind of a coordinate.
okay, because yes, this kind of coordinate change you'll be justifying later on, or it's.
Well, this is in a sense, this is what I mean when I say I focus in the infrared of the theory. So if I take this limit, I change these variables, take L to infinity, keeping this parameters fixed. So this is the limit you need to take. And it's not just for this specific kind of process. It's the same limit for all other amplitudes. Again, you was wait 2, 3 slides. Yes. Okay, so now if we put everything together, so we just recovered the energy momentum preserving delta functions. The momentum one was already manifest because I worked in CFT in momentum space. The energy came from these triple K integrals. And then we put together the rest. So the rest is coming from taking the specific, these tensors here. And then if you put everything together, that precisely recombines into d+1 momenta and polarization vectors. So this comes from this kinematics of the CFT. And the result reproduces in complete detail, including 2's and i's and pi's and sines of a result which was obtained over 50 years ago, where people who were doing it tried to compute the electromagnetic form factors of the W bosons. Actually, this is maybe the 3rd paper on that topic. There was one in the late 50s, one in the mid 60s. This gave the complete answer, and this result from the CFT directly reproduces that one. And the 3 constants, so I told you that a CFT in 3 dimensions, the CFT 3-point function in 3 dimensions involve 3 constants. These 3 constants are precisely the charge, magnetic moment, and quadruple moment.
The polarization vectors are related to the structural constants of the OPs?
No, these are related more to momenta and the tensors. That they're not related to OPs. This is related more to the kinematics that you get over there. And there is, again, if I had maybe another talk, I would have given more details. So the polarization vectors emerge from the boundary conditions you impose in ADS. So the source part of the field. I'm going to finish early on that, unless I have more questions. The polarization part of the source become a polarization vector in the limit. So the sources, the CFT sources, morph into polarization vectors in the limit. And this was done, you can show that in generality, not just the specific example that I mentioned there. Okay. So one can say, what's the big deal? I just reproduced something that was known for over 50 years, which is true. But I think also gives a bit more insight in the sense this these properties just come from properties of CFT in one dimension less. And this sort of unexpected relations could come also in other examples. So yesterday we had in the talk, this 28 over 20 factors. There could be some CFT relation in one dimension less that tells you why you have the number of adjustment relations you have. Okay, so this was the view from the CFT. Now I'm going to have one slide from the view from the ADS perspective, because that's the easiest thing to generalize to the general case. So we started the talk from ADS, we took the limit, we went to CFT, and then understood the limit in the CFT. But I could have done everything also in ADS. And the computation of the 3-point function in ADS is done via so-called Witten diagrams. So here is again ADS. So when you do computations in ADS CFT, you give boundary conditions at the boundary. And then you have bulk to boundary propagators that move these points to the interior. And then you have bulk vertices from the action, and then you integrate over all of ADS. So these modified Bessel functions that appear here are these bulk to boundary propagators. So usually in most of the ADS CFT literature, people done these computations in position space. But if you Fourier transform the bulk to boundary propagator, you get these modified Bessel functions. And then the integration over this bulk vertex is giving you this integration over here, where x now is the radial coordinate of ADS. So that's, in a sense, brings back to where we started from. I did the change of variables in the beginning to map ADS to Minkowski. And now I can do the same change of variables here in the context of the integrals. Okay. So this was the 3-point function. Now this is going to be very quick because it's just a nice picture. So suppose you're interested in some general amplitude. Here I have an 8-point function. So kind of 3 massive fields with 2 massless. Actually, it was in the talk was up to 8 yesterday. So that could be some of the things that we discussed yesterday in the last talk. And then the blob here indicates any loop order computation. So there would be bulk vertices and bulk propagators. And then the limit I discuss, you can do it kind of piece by piece. And then, so this is the corresponding amplitude in ADS, where now you have insertions in the boundary of ADS. And in the middle, you have arbitrary loop order. And then you can check that as you take the limit, these external legs here become plane waves in the limit, as you would expect from in kind of flat space scattering amplitudes. The bulk-to-bulk propagators that propagate in the middle become flat space propagators. And then in the limit, the interactions are kept fixed. So the integrand here maps immediately to the integrand over there. So this, taking the limit on ADS or in the corresponding CFT, directly yields for you the corresponding amplitude in flat space. Okay, so that's how things, this is the general perturbative case. Okay, so now let me summarize and conclude. So what I discussed today is a new way to compute scattering amplitudes for a deep +1 dimensional theory in flat space by taking a limit of CFT correlators in 1 dimension less. I think, if you didn't know about holography, I think this is surprising. And it is rooted in deep ideas about quantum gravity. This is just the beginning. I think there's still an enormous amount of things to be done. I mean, this is, again, a top-down approach. There has been a lot of interesting work in bottom-up approaches. I think one should connect and try to see how everything fits together. I think the last slide kind of sketch how to get all perturbative amplitudes, but this have the the potential to give non-perturbative results for scattering amplitudes, and I think it would be interesting to further pursue this. There are also many interesting approaches in scattering amplitudes themselves, like the things we've heard yesterday, or generalized unitarity and so on. It would be also interesting to connect that. Maybe one can also learn new things about CFTs from the lower dimensional perspective. But perhaps from the bigger picture, CFTs satisfy powerful constraints, so-called bootstrap equations, which in principle non-perturbatively determine the theory. And one could hope that one would be able to solve those. So if we're interested for, let's say, our universe, the aim should be three-dimensional CFTs. And this would determine who, because I start by postulating an effective action with some couplings. Clearly, not all of those will be part of a consistent theory. There is a swampland and a landscape, as we've heard yesterday. And now that formulates that question non-perturbatively. Some of these lower energy theories will be part of actual CFTs that satisfy the bootstrap equations, and some not. And that problem is much better defined because it's about CFTs that we fully understand. And it's about equations that, in principle, can be put in a computer and solved. And many, many, many other things. And just to finish off, I just want to put back again the slide I had earlier. Perhaps we have a new unification principle via the CFT that unifies all these different approaches. Yeah, thank you. So it is order, well, the CFT computation is non-perturbative because I haven't done perturbation theory. I just solved the CFT constraints. And the results, again, there are three numbers. And these three numbers are determined non-perturbatively. It's from the bulk perspective, if I in terms of.
So, I mean, if I want to ask you the CFT data. One moment.
If you know the CFT data, yes.
Which is, sorry.
Yeah.
If I'm going to ask you, what is the dipole moment, for example, of the W? What would be the answer?
Well, that would be, in a sense, the specific coupling which appears at the cubic order in low energy effective action.
So you can give a number to experimentalists on this, right?
I could give a number to experimentalists.
And now,
yes.
concerning something, concerning the renormalization, in this formula, this wave function renormalization or
yes.
not?
This is not the conventional wave function renormalization you would think from the perspective. No, this is renormalization of the CFT, the three-dimensional CFT, where you renormalize the operators. It's not the wave function renormalization of the four-dimensional theory. So,
okay. By the way, at the one loop, this is finite anyway.
This is finite to all orders. This specific guy, yes. Yeah, so this, in a sense, reproduces everything you've been known for these numbers, but now at an non-perturbative level.
And you can separate
in a sense, you need this rescaling not to, in a sense, you need it to get the limit how to go from a CFT to Minkowski space. It's part of the process. What do you do in the theory? I come as a CFT person, I tell you these are all the observables of the theory, these are the correlators. And now to those, you have to do an operation to get scattering amplitudes. This operation involves scaling the operators and then taking the limits in a specific way. Once you do all of that, the limit exists, in a sense it's a finite limit, and by construction gives you scattering amplitudes in one dimension higher.
that case, that theory, if you take the boundary CFT and you imply and impose bootstrap constraints,
So that would fail, not perturbatively.
Fixed ADS, I think in that case, you know you will get the bootstrap constraints, but that would be an quote-unquote non-local CFT because it will not have a threshold.
But may not be the theory in the sense we're interested in, right? In the sense, I want to start with the theory.
That's the one you're interested in because if you take, let's say, electrodynamics, quantum electrodynamics, and you look what is the dual, the boundary CFT, it will be a theory without the step, right?
No, why? The energy.
Because there is no graviton in quantum.
Oh yeah. So if you're interested in the low energies, of course. But of course, in our. Yes, yeah, but in our universe, there's also gravity. So in a sense, I want, in a sense, the results that applies. Of course, the gravity contribution is weak.
Right, but then you will not get a CFT that satisfies you.
Well, I may or may not. Maybe in a sense there are one or two, or maybe a handful that gives you a landscape. I think for me that's an interesting thing to know. It's.
Carlos.
So, but what do we know about the 3D CFT? Do we know? So, take this as you want, electrodynamics in energy, right?
Yeah.
Can we tell anything about the 3D CFT? What is that with which I will calculate all the things?
I mean, I know part of the properties that the CFT should have because I know the field content of the four-dimensional theory I'm interested in, let's say the standard model, and then I can translate this into part of the spectrum of the CFT and part of the OPE coefficient. Then once I have this partial information, then what I should do is to see if such a theory exists is to put it in the bootstrap equations with this data and see whether there exists an actual CFT that contains that subsector as part of it. And then whatever else it contains as part of what is the theory?
How would you know from the standard model the structure function?
I would know the 3-point functions. And the 3-point functions are related to the structure.
You don't know them exactly in the standard model.
Well, you will know in a sense you input the information you have. We have, let's say, trilinear couplings. We know the
It's at 3 level.
Perhaps the question is it a unique CFT that gives you the result?
I think in general, I expect there would be, in a sense, a landscape of theories that contain the standard model the way we know it.
The same limit.
In the low energy limit, we get that. There may be more kind of, or the dream would be there is only one, right? I give the data and then I put it in the computer, then Bootstrap runs for a couple of months and say one solution that has exactly.
People tried in 1980s.
I know, but that's a bit better defined than trying to find the right Columbia.
I think we all agree that the approach is unique and nice. Maybe it would be great to have more questions. θόρυβος μπορεί να εκνευρίσει την μελίτη. Okay, the last talk of the morning session is by Asimina Varnitaki on super radial interactions of cosmic noise.
Hi everyone, thank you very much for having me, and thank you very much for, as Costa said, thank you for organizing this amazing event that gives us a chance to get together. So for my talk, I will describe recent work that we did with Marius, whom you've heard of from yesterday morning. And Savas Dimopoulos, who is many of you know, of course, he's a professor at Stanford University. And what we set out to do with his work is enhance the interaction rate of things that interacts with us extremely rarely. Okay? Traditional, when we try to do searches for things like dark matter or proton decay, for example, what we build is huge detectors where the tiny cross-section that they have, or the tiny decay rate that the processes have, is enhanced by Avogadro's number, basically the number of particles in the detector. So the question we ask is, what processes, do we have processes whose interaction rate grows like the number of particles squared, which would be a huge boost in detectability. We already know of such an example. Okay, let me see. We already know of such an example, and that example is elastic scattering. We know in elastic scattering processes, and I will review them briefly, that you can have interaction rates that goes with the number of scatterers in the target squared. What we found, in fact, that you can have processes, in elastic processes, when you excite the internal degrees of freedom of your target, that can still grow like n squared, but that requires special conditions, as we will see. Now, this is a brief review. This may be very... this is a review of the elastic scattering case, which is, I suspect, in this audience, the thing that most people are familiar with. So let's imagine we have a mass, okay, an object, can be anything, gas, liquid, solid, that it's made up of n atoms, and we have an incoming particle wave, scatters from it, it goes out, and transfers, and it doesn't transfer any energy in principle. We call it elastic scattering. So the incoming momentum is equal to the outgoing momentum in magnitude. Now, there is still some momentum transfer because you've changed the direction of the momentum. And you find that if that momentum transfer is really small, basically proportional to the inverse size of the object, then the interaction rate grows like n squared, because now you cannot localize, if you think about the uncertainty principle, you cannot localize which atom you interacted from. Formally, each atom acquires the scattering phase in the scattering amplitude from each atom, and because that's proportional to the atom's position in the solid times the momentum transfer. And if the momentum transfer is small, that phase is 1, so all the scattering amplitudes add up coherently. Okay? So we've transferred a very small momentum transfer, and in fact, formally, we've also transferred some momentum to the object, but that momentum is tiny compared to the rest mass energy, okay? Now let's expand this picture, and as we know, atoms can have internal structures. So let's simplify their internal structure and assume that the scatterers are a two-level system. There is a ground state, there is an excited state. They're split by some energy split in omega naught. And we will consider two extreme possibilities. One where all the atoms start from the ground state, and one where all the atoms are in an equal superposition of ground and excited. Okay, and this is something that we know how to create experimentally. So now let's look at the following process. Let's look at what happens where we have a target of n atoms, where all the atoms start from the ground state, and we ask the question again, we try to calculate the scattering rate of an incoming particle wave from this target, and at the same time we demand, in the process that we care about, that the incoming particles excited a single atom. Okay? When you do that, you find, contrary to the case of the elastic scattering, that now the final states are orthogonal to each other. Okay? Because they are distinct states. Either you excited atom 1, 2, 3, etc. So now that means that the scattering rate from this process, where we still transfer very little momentum, but we also excited an atom, still grows like n. It doesn't grow like n squared. Okay? Let's now prepare the atoms in an equal superposition of ground and excited. And look at the same so now let's calculate the rate to excite, and this is what this arrow denotes. Each atom is in equal superposition of ground and excited. Let's calculate the probability that the one atom gets excited. Now, when we do that, and we decompose the excited state into the original state, you see that the excited state now is not orthogonal to the original state. So the final states of this problem are not orthogonal to each other, which means that now we have coherence. We've recovered coherence. So in the scattering amplitude, we can add coherently the contribution from each atom, so it grows like n, and that means now the rate goes like n squared. Okay? So we've achieved the point of this. We've achieved the interaction rates that we had in the elastic scattering case, but at the same time, we've managed to transfer a significant amount of energy to the atom, because the energy splitting, imagine that you can have EV energy splittings depending on what type of atomic transitions you look at, which can be much larger than whatever energy you transfer to the center of mass itself. Okay? Is this clear? Yeah, okay, good.
If you start instead of this particular combination,
Yeah.
random combination,
Yes.
some coefficient alpha, beta, what will happen?
It's the same. You just get I mean, this is what maximizes the rate. You just get it's a product. It's the amount. It's a product of there is an n squared, but it's weighted by the amount of a squared. Yeah, yeah. Square. Yeah. Still it's n squared, but it's to order 1. As long as alpha and beta are order 1, you get the same, and this is what maximized, and I took the extreme. Yeah.
If atoms are decoherent, of course that is understood, but what happens if all atoms are decoherent? That we will further enhance?
No. I don't know how to get more than n squared. Sorry. I don't know how to get more than n squared.
And this is independent of the energy of the incoming particle.
Good. That's an excellent question. No, it's not. Okay? Let's discuss. There is a subtlety with that, and I will come to that. Actually, this is my next slide, because that's a great question. Well, before we go to that, though, the reason that this is the type of interactions that I called superradiant in the beginning. And this is an analogy with decay superradiance, which is an effect that Decay found out about spontaneous decay of atoms. Okay, so this is from 1954, and our work is it's essentially a generalization of Decay's work. So if I have an atom that's prepared in this superposition, n atoms that are prepared in the equal superposition of ground and excited state, what he found is that the spontaneous emission rate, the lifetime of each atom, is enhanced. There is a cooperative effect, and it's enhanced by n. Okay? So sometimes in atomic physics, they call them cooperative effects, or this is something that in quantum optics people work with all the time. Okay? So they get a photon emission rate from these atoms that goes like n squared now. And you have similar effects in stimulated absorption and emission. Now let's go back to the question. So what are the, how does this coherence depend on the properties of the incoming particles and the properties of the system? So as I mentioned at the beginning of the case of the elastic scattering, and this is true for the case of inelastic scattering as well, each atom acquires a phase factor coming from the scattering. So there is an overall form factor that is the square of the sum of these phases, where Q is the momentum transfer, over all atoms. Now this behaves differently depending on the momentum transfer and the size of the system. So now let's look at, so this is a plot that shows in arbitrary units the total interaction rate as a function of the size of the system that contains, that is our target, okay, that has n atoms. Now, in the beginning, let's work with a system that's smaller than the wavelength of the incoming particle, the de Broglie wavelength of the incoming particle. In that case, you automatically couple to the whole system. The rate goes like n squared. This is for scattering of light. This is known as the Rayleigh regime of scattering. Okay, so this means that the interaction rate grows like the size to the 6. Now let's go to a regime where the object is bigger than the de Broglie wavelength, okay, of the incoming particle. Now, notice the following though. Naively, you would say, oh, you start losing coherence. In some ways you do, but not really, because if you see here, what enters in the scattering form factor is the momentum transfer. So in fact, independent of what the de Broglie wavelength of the scattering particle is, as long as the Born approximation applies, you're in the weak scattering limit, you find that your rate, in principle, as long as the momentum transfer is small, you still grow like n squared. But now, because this can only happen when you scatter, you have small momentum transfer. So in the forward direction, you get a suppression that goes like the solid angle. That goes like lambda squared, the de Broglie wavelength, divided by the size squared of the object. But you see still here that you still gain like r to the 4th. So you still gain compared to the r cubed of the incoherent contribution. Now, because we're talking about inelastic processes, and in inelastic processes, because we transfer some energy to the atom, it's a significant amount of energy, that energy comes from the scattering particle itself. So there is always some minimum momentum change on the particle, okay? So when we cross that threshold, this is where we really start losing coherence, and the interaction rate grows like r squared. It's still much larger than the incoherent contribution, okay? And in the elastic case, this line is never there, and in fact, you reach the r squared regime only when the Born approximation breaks down, okay? Does that make sense? Good. So now let's go and calculate some example rates, okay? And I will start by the cosmic neutrino background, discuss axioms and other things. The reason that we went down the path of trying to enhance the interaction rate of cosmic relics is because of a relic that's been kind of like a holy grail in particle physics, which is known as the cosmic neutrino background. And given that the composition of the audience, I assume for many of you this is a known story, let's see where this thing is coming from. Now, this is a picture that shows the traditional, what we know to be the standard picture of cosmology. There was a Big Bang, universe expanding through inflation, it reheated, it was hot, and as it evolved, it became bigger. At the same time, it cooled down. Eventually, protons formed, atoms formed, and galaxies formed, and here we are 10 billion years later. Now, a special time is the time where atoms form, and this is where the time the universe became transparent to photons. This happened when the universe was about 400,000 years old, and this is a picture of the cosmic, and this is what is known as the cosmic microwave background. Its temperature is roughly, it's the frequency, as the name suggests, of microwave, is 2.4 Kelvin. And this is the picture from the Planck satellite. And it's a milestone. Its discovery and precision measurement of the cosmic microwave background, it's a milestone because it allowed us to turn cosmology into precision science. In fact, now we know the composition of the universe to the percent level, okay? Which is a remarkable feat. Now let's go back in time. And there is another time where the universe became transparent to the partners of the electron, the electroweak partners of the electron, the neutrinos. And because these guys interact very weakly with us, more weakly than the photons, the universe became transparent to them roughly when the universe was a second old. And those relic neutrinos are still zooming around today. They decoupled from the expansion of the universe when they were very hot, at a temperature of roughly an MeV. Okay? But today, because the universe has expanded, they're just slogging around with a fraction of the speed of light. In fact, they are the most abundant cosmological relic of neutrinos that we have. They are the only non-relativistic, significantly non-relativistic component, neutrino component that we'll ever create, because neutrinos, because they are associated with the weak interactions, they're always created in radioactive processes, in violent stellar environments, so they are always highly boosted, okay? So their average momentum is really small. So if you convert it to the Broglie's wavelength, you find something that's 2 millimeters. Just to give you an idea, the neutrinos that are produced in reactors are a few times bigger than a big nucleus. Okay, so we're talking about orders and orders of magnitude of hierarchies between scales. They have very little energy, and that's part of the problem. Because they have so little energy, when they interact with matter, their cross-section is tiny, so much so that essentially they go through the entire universe without interacting once. As I told you before, they are the most abundant. In fact, they are almost as abundant as the cosmic microwave background photons. So just a mnemonic at the tip of your finger, you have roughly 100 of them at any given time. Per flavor, we have 3 flavors, the electron, the muon, and the tau flavors of neutrinos. Now I hope it's obvious now what's important. So it's an analog of the CMB, but coming from a much earlier time. So if we were to detect it, we would get some sort of information, the earliest available to us, experimentally, about the universe, because we would get a snapshot of the universe of how it looked like when it was 1 second old. Now neutrinos are also the least explored. Actually, I shouldn't say explored, because they interact so weakly, they're hard to measure. So their parameters are not as well measured at all as other standard model parameters. And there are other things that come with them. For example, the fact that they are created non-relativistically by what the universe has given us. If we were to discover them, which we would celebrate, then we would use them as a tool, like we do everything. So because they move so slowly, now, for example, the cosmic microwave background moves with the speed of light. So in order to reach us, it has traveled 10, 30 gigaparsec of distance, 10 billion years, light years. These guys, if they are when they are non-relativistic, moving with a fraction of the speed of light, they only come from a nearby vicinity, 1 megaparsec, 1 gigaparsec. So you get, even though they were created very early, they are like, can provide, depending on their velocity, a 3D photomography of the universe, okay? So their surface, the surface of last scattering for neutrinos is not really a surface, it's a volume, okay? So if we were able to detect them in a laboratory setting, that would be actually an amazing feat. So what did we consider? So the interaction we care about these guys now, and it will be relevant for us, the two-level system that is interesting for the energy that these neutrinos carry are essentially nuclear spins put in a strong magnetic field. So if you put spins in a magnetic field, spin up and spin down are split by some amount that you can dial depending on the strength of the magnetic field. And that gives you the two-level system. So we take n spins, put them in an equal superposition of ground and excited, and now we want to calculate the interaction rate of the cosmic neutrino background with those spins. No, in the lab. Neutron star, I cannot send graduate students there, sorry. Yes. The nuclei doesn't matter. Yeah, it's the same, because for that low energy, there's nuclear magnetic resonance, right? So when you go get an MRI, that's the technology, okay? Yeah, because you don't excite the internal structure, so you can treat the atom as a whole. So even if you talk about the nucleus or the atom, it doesn't matter, given the energies. They are very low energies that I'm going to be talking about. Yeah. More questions? Yes?
How big do you need this to be?
Okay, I'll come to that just in a minute. It depends on the rate you can detect, but you will see. So the processes that are of interest for the cosmic neutrinos are two. So you can have a cosmic neutrino come in this, interact with the n spins, deposit some of its kinetic energy, and go out and excite the atom, okay? Or the nucleus, or whatever your two-level system is. There is another interesting case, actually, that is very special to neutrinos, and I will come and explain that more. You can also have the case where a heavy neutrino transfers some of its rest mass energy, not its kinetic energy now, rest mass energy, converts to a lighter neutrino, and then excites a spin, excites the two-level system, okay? And I will explain why this is special to the cosmic neutrinos. So let's start with a case of having a neutrino that doesn't transmute, that doesn't change its nature. So the maximum, so if the energy that you use to excite comes from the neutrino, there is a maximum value depending on the neutrino mass that you have, and that's about 10 to the minus 6 eV, okay? Just to give you an idea, the average energy of a cosmic microwave background photon is about 10 to the minus 4 eV. So it's 100 times less than that. Now, in order to couple, so we take the spins, they cannot be put all in the same point. They will have an extent. And in order to, again, in reality, we won't be able to take it to advantage of the full energy available to us, because we will need to get the n squared to have a very small momentum transfer. So if we require that the momentum transfer of the inverse size of the object that we use, it actually puts an upper bound on the energy transfer we can have and still maintain coherence. And if you do energy conservation, you find that the maximum energy splitting between the spins has to be less than the velocity of the neutrinos divided by the size. And for the numbers that we took, we assume a size of 10 centimeters. So this is an object that's this big. Okay? So, and with liquid or solid state density of spins, this is the rates that you get. This plot shows the total rate, which is the sum of excitation and de-excitation, because these two processes will happen at the same time. Okay? You can both excite and de-excite. And this is the de-excitation rate in hertz, okay, as a function of the energy splitting between the spins. So let's take, for an object now that's 10 centimeters, you find that the coherent interaction rate is a fraction of a hertz. So you get one interaction roughly every 5 seconds. Now, if you didn't have the coherence, you would have one interaction every 10 to the 4 times the lifetime of the universe. Okay? So coherence gives you a huge boost. Avogadro's number is a huge number. It's 10 to the 20. Okay? So this is where we get all our money from. Yeah. Good. So so this would be, it depends on the magnetic moment. So this would be here the maximum. You can get about 10 to 20 Tesla. So this is the extreme. So here it would be about 0.1 Tesla, which is easily achievable. So yeah, it depends on the type of spin you use, and we're thinking of, for experimental reasons, in principle you could do it for electron spins as well. So the magnetic moment is larger, but for nuclear spins, this is about 10 Tesla field. Okay. Now you see here that the rate for 1 centimeter, which is this size, okay, is 10 to the 4 times smaller than the 10 centimeter. So now again, the other thing that you see is that if you keep the size fixed and start changing the excitation energy, which you can do by changing the magnetic field, you see that you can change the rate by order 1. So your excitation energy is a control parameter that can turn on and off coherence at will. Now, the interesting thing is, so usually in particle physics, when we talk about observables, a lot of the time we really mean energy transfer, because this is what we're good at measuring. And there are cases where coherence can cancel in net energy transfer, but in this case it doesn't happen in scattering. So, and the reason it doesn't happen is because the neutrinos have a distribution, a thermal-like distribution, so there is a phase space factor. So because of that phase space, there is always some net energy transfer from the neutrino background to your detector. And that, compared to the total rate, turns out the phase space factor goes at the ratio of the de Broglie wavelength to the size, to the 1 power. And this is at the maximum here. So when you go to lower excitation energies, the phase space factor becomes proportional to the splitting energy and goes to 0 as you go to zero energy splitting. Okay? Now, this is the cool part that can happen for neutrinos. So neutrinos, exactly because they are so light and because they're so weakly interacting, the universe is populated, in fact, by 3 mass eigenstates, all 3 of them, heaviest to lightest, and these are not the same as the interaction eigenstates. Okay, Now, naively, you would say everything should have decayed to the lightest state. That's the expectation we have. But the lifetime to decay of the heavy guy to decay to the lighter guy is so long that we find ourselves in a way in an out of equilibrium path of neutrinos. So this is why we can have processes like this, where the heavy neutrino comes in, deposits some of it, changes its rest mass, and its rest mass now is available to excite the atom. Okay? Of course, the rate of this depends on the type of neutrino mass hierarchy, which I don't have time to explain. There is inverted, there is normal hierarchy. The best case scenario is the inverted mass hierarchy, and the largest rates you get from the transition of the heaviest guy to the next lightest guy. And now you get something like this if you plot the total interaction rate again for cosmic neutrinos as a function now of the excitation energy. Now you see that the energies now are much larger than what we talked about before. This is for the inverted mass hierarchy, yes. Sorry, this is after, well, hopefully. I mean, I actually, to tell you this truth, this excitation energy, this is a theoretical calculation. Experimental is going to be very hard because of the properties of the electron spin. So here, to get to these energies, you have to put spins in electron spins in a large B field. In nuclear spins, you would need 1,000 Tesla fields, which, I mean, but for electron spins, you can. The problem is experimentally, they're hard to do the type of experiments that you need to see this. Okay, and I'll come to this towards the end. Now, the interesting thing is that when the excitation energy is basically exactly the mass splitting, you recover full coherence. When you're a bit away from this optimal energy splitting, coherence gets lost very quickly because the outgoing neutrino either doesn't have enough energy to be produced, or it becomes too relativistic. So Q becomes very large, okay, in this process. So that's why it looks like an absorption line, this type of rate. So again, this omega naught is a powerful tool to be able to distinguish these things. Now, there is still the net rate is non-zero. And the net rate, actually, whether you have positive energy exchange or negative energy exchange, it depends on whether you are on the left or the right of the optimal energy. And you can get positive energy exchange with the CNUB exactly because you're in this out of equilibrium situation for neutrinos, which is quite unique, actually, in fact. If I were to design a dark matter model that would do this, or any other model, I would have to stand on my head and do backflips to make it work. So neutrinos do this for free in a way. Now, what other things can you do with this? So the superradiant interactions are very general. So another interesting thing you can do absorption rates. You can do absorption processes or emission processes, which is very similar to what Dicke did, but for photons. Now, the particles that are relevant for this, how much time do I have? Ah, okay, good. So one of those things is that you can potentially detect are axions. And perhaps the most famous of those is the QCD axion. So axions were proposed back in the late 70s, early 80s to explain why the electric dipole moment of the neutron is so small. Okay? So in the standard model, you can add a term that mixes the electric field of the strong interactions and the magnetic field of the strong interactions. And this is a CP violating term, whose effects are parameterized by this angle theta. So CP is not a good symmetry in the standard model. So people, to explain why this theta parameter is so small, they convert it to a dynamical field whose cosmological evolution naturally relaxes this value close to 0. This dynamical field is predicted to be extremely light, okay, much lighter than any of the other standard model particles, and its properties are uniquely defined by the axion decay constant. This one parameter. So if, for example, you have a decay constant close to the Planck scale, you have a Compton wavelength of these particles, which is kilometer in size. So we're talking about extremely, extremely light particles. Turns out that you go into extensions of the standard the standard model, like string theory, and try to embed the QCD axion in it. You find that the axion comes with particles that have a lot of the same properties. And in fact, this happens because string theory has three, as we've heard in many talks, three fundamental ingredients. You need extra dimensions to make the theory mathematically consistent. You have gauge fields that live in these extra dimensions. And you have topology. Basically, the shape and size you need to compactify these extra dimensions to give rise to our four-dimensional world. So the more complex the compactification, the more particles you get in 4D that manifest themselves as axions, particles that have very similar properties to the QCD axion. In fact, you can also get particles that have similar properties to the photon. People call them dark photons, spin-1 particles. And there are also particles, this is parenthetical, that you may have heard, like dilatons, moduli in the radion, that couple extremely weakly to us, and can be also light, just as the QCD axion. Now, for what we care about, given that we talk about spins, the coupling that's relevant for us is the couplings of axions, which are pseudoscalar particles. And if I stick to the Hertz rate that I was talking about for neutrinos and try to draw what the Hertz rate contours would be in a plot that shows the axion coupling as a function of the mass, I would get Hertz rates not with an object. Just to give you an idea, this also tells you how weakly the CNUB interacts. So in order to get a Hertz rate, I needed 10 centimeter size object for the CNUB. I can get the same rate for axions, if I just want to beat the astrophysical constraints, with an object that's about a fraction of a micron wide. Okay? So we're talking about something that's thin, smaller than the width of a human hair. Okay? This is what coherence, again, this is a lot what coherence buys you. If you make the sample a bit bigger, then the rate, the 1 Hertz contour rate, start probing the line that corresponds to that of the QCD axion. Now I should say there is a similar plot you can draw for dark photons. I should say it's crucial here to talk about the total rate, okay? Because if I were to calculate the sum of excitation, the excitation rate, this will almost cancel out to 0. So I need to find ways not to stick to direct energy exchange because I will be hurting myself a lot. So I need to find ways to actually measure the sum of the rates. Now the other thing before I go on, given that the coherence does not depend on the actual wavelength of the particle, we asked ourselves what other neutrino sources we can detect. So for a while, we were actually thinking that you maybe detect nuclear activity around the globe. So because these detectors in principle are very small, you can imagine that you want to check on people that do things you don't want to do without asking their permission. Okay? So, yeah, like, or Russians. So it turns out that maybe harder than the neutrino, cosmic neutrino case, in fact. So if you want to detect, let's say, a megaton bomb, which is, actually, it's very hard to do these estimates because no one has any idea. You don't Google neutrino production nuclear bombs and get an exact number, okay? So if you extrapolate what the reactor activity is in terms of energy released in bombs, you will probably need like a meter-sized object, like this big, if you want to detect a bomb going off 1,000 kilometers away. So 1,000 kilometers now becomes, I put a few around the globe and I can see anything everywhere, okay? Yeah, that may be a bit tough, but still fun to think about. So now let's talk about how would you measure this, okay? I've done theoretical calculations, but I've never told you how, in principle, you would measure it. So in order to make all use of everything, I will need to look at, let me skip this, at the full energy exchange. I will need to look not as just energy exchange, I will need to look at the total interaction rate. So the way people, let's go back to talking about the state of the spins, or any two-level system, in fact. And the way people represent these states are what is known as the Bloch sphere. So in the states of n atoms in a Bloch sphere is represented by a vector of length n, where n is the number of atoms. If the vector is pointing to the south pole of the sphere, this means all the atoms are in the ground state. If it's on the north pole, every atom is in the excited state. And anything on the equator means that this vector, the atoms are in linear superposition of ground and excited, and there is a phase multiplying with a relative phase. Okay? So the energy, what measures the energy in the system is the coordinate in the z-axis, which is this axis here, north to south pole. So you can see that if I measure this distance, tells me how many atoms I have in the excited state. So it tells me how many atoms have how much energy stored in the atoms. So if I want to measure energy exchange, I would just measure this position here. Okay? And if I were to calculate the signal to noise ratio for this process, starting from all atoms pointing in the ground state or atoms in an equal superposition of ground and excited, you will see that if I have a net energy exchange, my signal to noise ratio grows faster in the case where atoms are in the product state. Okay? So already it tells you that if I prepare atoms, which experimentalists know how to prepare this very well, it's just a Rabi oscillation of the system, I already have a gain. So you can see this by doing a bit of an unfair comparison with an existing experiment. Okay, Catherine is an experiment that is in Karlsruhe that has been designed to measure the mass, the endpoint decay of tritium. So it's trying to measure the mass of the neutrino. They've done in that experiment a search for the cosmic neutrino background. And they placed a constraint. They were never able to reach the sensitivity required. They are roughly 10 to 11 orders of magnitude off. Okay? You can actually get the same type of sensitivity as Catherine, which is this experiment right here. In fact, so the experiment was built 700 kilometers from Karlsruhe, but they had to move it. And they had to move it, they couldn't move it the entire distance, so they had to take it through the Danube, do roughly some thousand of kilometers of like circle, and the last 70 kilometers they had to take through little villages in the area. So this is an actual picture. This is not a photoshopped picture. Okay, and this gives you the scale of the experiment as well. So if I were to take the 10 centimeter objects that we discussed, apply a pi over 2 pulse that experimentalists know how to do, and convert that to a constraint on the cosmic neutrino background density, I would find the same thing that Catherine does with huge size. Okay? So this gives you, it's a direct points to that coherence does help you a lot.
What size do you need to get the same as scattering?
So this is 10 centimeters. So this is this big.
And what size do you need to measure what scattering is looking?
I mean, that's the mass spectrometer. So you need this, how much is that? 10 meters?
Why did you have to move it around?
Because they couldn't get it through the roads, right? So they had to take it on the Danube, which is a huge river, and the last thing they had to pick the route so that it fits between the houses. I'm not sure, part of it maybe, but
They moved it around, put it on the side, they built it somewhere else.
yeah, they had to move it to the actual Karlsruhe location.
Now, why they didn't build it on the side?
I don't know that. Don't ask me that. I don't know. I'm not an experimentalist. That's fine. Yeah, that would be maybe they had the parts there. Look, I know sometimes they have, I know, for example, they moved an experiment from Brookhaven to Fermilab. So experimentalists do that. If you have a device somewhere that's already built, I mean, you won't bother to build it because usually they are a bit expensive too.
Some people knew how to build it. The Germans paid, and then they said, we want it.
There you go. So now let's talk about measuring the net rate. So the total rate. So now think about each interaction as a discrete event. So if I have, let's say, the interaction rate, the excitation rate, and the de-excitation rate are exactly the same, but because they are discrete events, I would have a random walk. So if I were to able to measure the random walk in the z-axis, measuring jz squared, that quantity would be sensitive to the sum. Now, those start complications. So if you calculate the signal to noise ratio that you get if you start from everything to the ground state and the excited state and the product state, which is half excited, half ground, you will see that your SNR actually you haven't gained much because here you have a huge uncertainty in Jz squared. So there is a square root of n uncertainty in the value of Jz. Okay, so that you haven't gained much, which means that if you want to talk about the total rate, you need to prepare special states. The extreme of those are the decay states that Dickey described in his 54 papers, which are energy eigenstates of the n atoms. And these are basically entangled atoms. Now, in the Bloch sphere, they're just a circle. They have a perfectly well-defined Jz value, but their phase is unknown. So the state representation on the Bloch sphere looks like this. Now you recover the n-square gains. The problem is now, these are hard to prepare. The best thing you can do is something in between, where you can, what the quantum optics they call squeezing of states, and which is somewhere between the product state and the decay state. And this is exactly what we're doing now. So we want to see how close can you get in realistic setups, close to the decay state, and see how well eventually you can do for at least a toy model, to have what people are calling a quantum protocol in the detector, in metrology. And this is where we're at now. So to conclude, superradiant interactions show that you can have interaction rates that grow like the number of atoms squared, while at the same time transferring a significant amount of energy, which gives you huge gains in interaction rates. For us, the goal would be the cosmic neutrino background. Interestingly enough, dark matter searches for axions and other things could also benefit a lot as a byproduct of this. And the interesting thing, though, you have to focus on observables that go beyond the traditional energy transfer. And this is what we're working on. And for us, this is just the beginning. So we are currently thinking of these protocols, and we want to see how far, are there other situations where these can be expanded further. So thank you. Yes. Question.
The energies that we're talking about are microwave, right?
Yeah, roughly.
Yeah. I mean, and you would need to cool this thing
Good.
because at microwave you have tons of excitations in a system
Mhm.
that can really screw up your.
Yeah, so good. So we think, so the spins for nuclear spins, okay, so this goes into the discussions that we're having now with experimentalists. So in fact, in order to make this work, actually it may be useful to show this plot. So the setup that given that we're talking about microwaves or very long wavelength photons, we won't be the system, the way we'll be reading out the system is not in electromagnetic cavity, it's with an LC circuit. So in order to do all what we want, the LC circuit needs to be far detuned from the spins. Okay, that's very important to have frequency separation. Now that's one. The good things about nuclear spins is because they are so well isolated from the environment, you have techniques where you can effectively put them in zero temperature or very close to the ground state. One, great. Now, because of the detuning, we've talked to experimentalists, we think that the thermal photons won't be affecting the spins in any harmful way. And they think they can there is ways also to even those, the quanta in the circuit to get them almost to zero temperature, but it's not clear that they would need to because of the decoupling of the two frequencies. It may not be necessary. And for the parameters that we care about, and we're thinking about frequencies of we're talking about 100 to 1,000 quanta in the circuit, just to give you a number. So, I mean, but we are looking at this actively. But it's a good question, though. Yeah.
There are pulsed magnetic fields up to 100 Tesla. Can these be used?
As far as we know, no, because it's exactly this. You need a constant field. You need to have the system very stable and have the energy splitting very stable. These are actually very short-lived. Like ridiculously short-lived, like not even a second. Like, yeah.
Quick second question.
Yeah.
Does this superradiance have anything to do with the superradiance around Earth?
No. Excellent. So thank you for asking. People use these two words for very different things, but they're not the same. Yes?
Thank you for this inspiring talk. My question is, nuclear spins interact via the electrons, for example.
Good.
Does that bother you?
No. Turns out the answer is no. So they do, there are timescales, so they do affect the properties of the system. So interactions, spin-spin interactions with the atoms and everything. There is these timescales called T1 and T2 for nuclear magnetic resonance systems that depend on these things. So as long as you are in a liquid form or gaseous form, and you have, I mean, I don't want to go to the details. We can discuss them more later of where they come from. But as long as you have small magnetic field gradients across the sample, these would be longer than 1,000 seconds or something. So they can be extremely long, enough for you to do the experiment and not having to worry about these things. Yeah.
What about multiple interactions of neutrinos? I mean, you said there are 100 on each on my finger.
Yeah, G Fermi is just so small. Just G Fermi sucks. Like it's just so small. We're still in the multiple interactions would mean a breakdown of the Born approximation. I would have to build an object that's about 1,000 meters big for me to worry about that in solid state density. So I would need a kilometer-sized object where multiple interactions are. I wish there were an issue. I really wish there were an issue. Yeah. Yeah.
Even if somebody that in order for this to work, you need something that would be in coherent state, but in a macroscopic distance.
Yeah, so the thing is that, yes, this is true. In a 10 centimeters, so you would have a decay state that's 10 centimeters big. It's not a problem. As long as gradients are small, dephasings are small, the disadvantage of nuclear spins, which make them, they are hard to manipulate, they're hard to polarize, is also an advantage. If you overcome the issue of polarization, then they are very well isolated from their environment for a long time. So, I mean, we have to look into this and see how there will be eventually limitations on how close to this perfectly equatorial state we can get, the decay equatorial state. And this is exactly what we're looking into now. But you can do a lot. You can do a lot, we think. Yeah. Good. We're trying to look into this a bit more carefully, but it's not clear. There is always, you're going to have, the form factors are what the important thing. And Bose-Einstein condensates are hard to deal with unless you deal with them in a solid state. If you try to build them out of atoms, you get too few, and we want a lot. So, so yeah, but it is a good question. We don't think so. We're thinking a bit more. Yeah, but yeah. Poti?
Thank you for a very nice talk and informative talk. So I have maybe a naive question, but
Yeah.
in the surface of dark matter, in the
Yeah.
direct detection,
Yeah.
sometimes you can reach the neutrino plot. Is it a possibility to use this machine just to somehow pick up this?
Yeah, sure. Okay, I have a backup slide. In our paper, we had everything. So we had dark matter, so you can, like anything, it's not a question of wavelength, right, to get coherence. So you can look for anything. The question is, do you have enough flux? So the key point of this, do you get enough flux? And this is a plot. I mean, this is not any. This is an agnostic, let's say, model of dark matter, which I hate the word. I don't know what type of dark matter this would be. I don't know how to get it. But in principle, you can make an axis, two axes, and make a plot. So you can get huge rates. Like if you take astrophysical constraint, I mean, yes, you can do it for dark matter rates as well. So anything. Yeah, anything. So.
Okay, let's thank Sasimina. It's a tradition of this series to be a bit late to the program. Let's have a really half an hour break and be here just before 12.
If I talk like this, can people in the back hear me? No. Okay? Yeah? Okay, okay. All right, so thanks very much. Thanks for the invitation, thanks for organizing. I admire this city very much. So let's go. This, as you can see from the title, is a talk on ADS-CFT. The idea of the talk is going to be using holography. The aim will be to discuss some UV conformal theories, I will describe in particular, leading the form and leading to confinement, and then leading to screening, some screening like that. So the plan will be to deal with an infinite family of n equals 2 conformal theories, 8 Poincaré supersymmetries. This can be done, what I'm going to describe can be done in 3, 4, 5, and 6 dimensions. I will focus on the 4-dimensional situation here, and then break conformality by a vacuum expectation value. This will lead to a gap system. It will preserve less supersymmetry. I will focus on one example in 4 dimensions and trying to get physics out of it.
How do you measure the supersymmetry?
You calculate in the background.
How do you measure the supersymmetry in different dimensions?
It will always, in the different dimensions, what I will discuss generically works when you have 8 Poincaré supersymmetries. Okay? So it's what you may call n equals 2. In 5 dimensions, you call n equals 1. In 6, you call n equals 1, 0, but 8 Poincaré. And like this comment, there are many technical aspects that I'll try to not mention so much and try to focus more on the ideas, showing not so many of the technical details. Talk is based on works in the last year with many PhD students, postdocs, and faculty in different combinations, right? So there is different papers all put together. So let's go a bit more. So let me start, because of the nature of the audience, with a generic introduction, and then we'll become a bit more technical as we go. So 1997, Maldacena conjectures the equivalence between CFTs, let me pick on the case of n equals 4 super-Young mills, and strings on ADS space, let me pick on the case of ADS 5 processors. There are 2 more examples in the Maldacena paper, but let's pick on them. Many developments follow. For example, how to calculate correlation functions. These are some very representative papers. How to extend the conjecture to non-conformal situations with different amount of SUSY. These are first initial papers that trigger a lot of activity. How to apply this conjecture to quantum field theories with immediate phenomenological relevance without so much emphasis on the stringing, embedding. By immediate phenomenological reference, I mean QCD or systems in condensed matter, and these are some of the papers that trigger lots of activity following from this. In this talk, I'll focus mostly on the first and the second items, how to learn about quantum field theories with different amount of SUSY in different dimensions, systems with many scales. Okay? So the plan of this talk is the following. First, I will try to describe the physics problem I will try to address. That will be how to write duals to theories like Young-Mills or QCD, or in general theories with a mass gap. Which are the unwelcome features in the models that already exist, that people have already worked out? And these unwelcome features are going to be either singularities in the supergravity description. This invalidates to do the calculations that one does, or some stringy-like non-field theoretical behaviors. Okay? And then I will try to mention how to cure these unwelcome features. I'll focus on one example that will be a family of 4D CFTs in the UV. After event deformation, they flow into a gap IR quantum field theory. I'll calculate some observables, and then we'll close. I'll have time to stop for questions, so if you want to ask me, and I'll try to answer to the rest of my knowledge. So let me start to set the problem, telling something 20 years old, that is how people, since the early 2000s, try to construct duals to field theories that are QCD-like or Young-Mills-like supersymmetric extensions of them. There are basically 3 lines, 3 three lines of attack to this problem that people have done, people have worked out. In the first line, this is conceptually the cleanest. You start with n equals 4 super Young Mills, so a very special conformal theory, and you deform it either by a relevant operator or a bed of a relevant operator. This triggers a flow into some interesting infrared pieces, characteristically strongly coupled and typically very interesting. The way this is holographically model is with a solution in this case in type 2B that is asymptotically ADS5 times S5 with some units of Ramond flux, with subleading other fields in the type 2B supergravity. These subleading fields make a flow in the geometry, namely a deformation of the metric, and characteristically what was happening in this way of attacking the problem, these are some representative papers, is that the end of this flow was in a singular metric. The fact that it's a singular metric tells you that the way you calculate in gravity is not trustably obtaining the results of this infrared field, right? So this is a problem in this type of approaches, namely the UV is very nicely well-defined and conceptually very Wilsonian, but when you go to the AR, you should not trust some of the results you get from it. Okay, so this is one type of approach. A second type of approach was it's a bit more technical, was considering a two-node conformal field theory, strongly coupled conformal field theory, and making a deformation of it. The field theory is written here. If this little number m is 0, this particular field theory is n equals 1 supersymmetric with a given superpotential, is strongly coupled conformal fixed point. You make a deformation by this imbalance between the gauge groups, and in this situation, whenever these two numbers n and m are related by an integer, so they are commensurate, the flow to the infrared is very well understood in field theory. It's a very nice story going on there, and you end up in an infrared theory that is an SUM gauge group with some Goldstone multiple. All these dynamics is captured by a type 2B, in this case, supergravity background. I don't need you to keep anything in mind about this, except that there are 4 dimensions and some internal 6-dimensional space. This 6-dimensional space knows everything about the RG flow and the global symmetries of this field theory. That's how things are encoded. And the only thing to keep in mind here is that at the end of the space, when you go, say, to the infrared of the field theory, the space is perfectly smooth. So anything you calculate with this approach will give you trustably about, will tell you trustably about the infrared strongly coupled dynamics there. But the only ugly thing here is that as you go to the UV of the field theory, you do not reach specifically strictly what's called an asymptotical ADS point, making the calculation of correlation functions a bit laborious. Okay, so it's technically a bit ugly.
Sorry,
Please.
what can you compute here in the infrared that is wrong compared to what you can compute there?
I think nothing. So that's why trustably this calculates things about this infrared. In this case, instead, this can calculate things that you should not trust regarding this infrared, because it's singular. For example, the Wilson loop, right? Or any observable. You will be able in this Petrini Girardero, Petrini Borrati and Zaffaroni, or the uplift that constant lift, to put some observable that basically goes to the singular point and gives you a result that.
But this is independency actually.
Yeah, because, okay, so basically this singularity is producing that onto you. Another idea that people had was to study deep brains, higher dimensional brains, D4, D5, D6, compactify them on certain manifolds, leading to, at low energies, field theories in 3 plus 1 or 2 plus 1 or 1 plus 1, different number of supersymmetries. Many people work on this. The idea is represented here. Take a higher dimensional deep brain, D4, D5, D6, compactify it, end up at low energies in a 3 plus 1 or 2 plus 1, etc. field theory. There is a very well-defined metric, many times completely explicit, that again in the infrared captures trustably the dynamics of this, but in the UV presents behaviors that are non-field theoretical. So basically you do not reach characteristically a UV fixed point in these setups, making the calculation of correlation functions laborious. Okay? So these are the three types of setups people have attempted in the last many years. And the features of these are, if the UV is well defined, like in the first type of setups, the infrared is typically singular. If the infrared is smooth, the UV is not strictly asymptotically ABS5 or ABS, and in some cases the UV is not field theoretical. Also, another feature is that if you want to add to these systems a large amount of matter transforming in the fundamental, namely quarks, this is quite technically challenging. I'm not saying it's impossible, I'm saying it's technically challenging, and it has some effects. But aside from all these nasty things, ugly things that I'm mentioning, there are numerous things that were calculated from these holographic duals, and lots of important lessons were learned. So the goal, the aim of this talk is to ask, or to try to answer the following question. Would it be possible to keep the virtues, like the smooth IR, repair the UV, making it asymptotical ABS, and also add flavors in a large number genetically? And this is the question that this talk tries to address. Before I go into how to keep this, let me stop here for any question or comment that people may have. And I think what? Go? All right. Okay. Very good. So the strategy is going to be the following. How to fix these issues, keeping the virtues that one would like to keep. So the idea will be, first consider a quantum field theory. This is where we start paying the price, as you will see. Consider a particular set of quantum field theories with fields in the adjoint, in the fundamental, and in the right fundamental, and write the known holographic dual. I will discuss these holographic duals in a couple of slides. Okay? But you will see that it's here where we lose the freedom of choosing any theory. Use then these superconformal theories, there is an infinite family of them, as UV fixed points. These UV fixed points will be deformed in the case of this talk by a bed. They could be deformed by a relevant operator, such that the infrared of the field theory will be smooth. The infrared of the supergravity corresponding to the infrared of the field theory will be smooth. Also preserve some supersymmetry, be a mixing, a twisting between the R symmetry of the field theory and the Lorentz group. Right? So in plots, the idea is the following. Start with some conformal field theory, with some R symmetry, compactify one direction of the conformal field theory on a circle, and do this compactification in such a way there is a mixing between the isometries of that circle and the R symmetry. This is just for the purpose of preserving some supersymmetry, which is just for the purpose of ensuring the stability of this situation. Right? So basically postponing or preventing the question about is this stable or not. This will be related to or realized by a holographic system that will be a quantum field theory, a cigar-like direction that mixes with the internal space, and the example we are going to discuss is a superconformal field theory in 4 dimensions with some asymmetry, compactified to 3 dimensions on a circle that will lead to a holographic background with a 3D part, a cigar-like direction, and some internal space. The infrared of the supergravity will be smooth. The UV will be asymptotically ABS I'm going to describe now, this becomes a bit more technical, is the 4D family of n equals 2 superconformal theories I'll use as heuristics point to the formula. So the theories I would like, and this is where I'm saying we are paying the price here, the theories I would like to discuss, they are what I call a quiver field theory, SUN1, SUN2 up to SUNP, with by fundamental matter joining these gauge groups, and also fundamental matter. Okay? These theories will be, in the particular case of this talk, n equals 2 field theories. If we want the theory to be conformal, and we will impose conditions for this to be, it has to happen that the global symmetries of this theory are, the bosonic part of the global symmetries are the conformal group in 4 dimensions, and because of the number of supersymmetries, some SU2 times U1 RC. Okay? So let's keep this in mind because they will reappear. The holographic background will contain an ADS file, a sphere, and a circle to realize precisely this global symmetry. One thing I would like to remind you, many of you are very familiar with this, and that's why I'm picking this 4D n equals 2 situation, that these theories are conformal whenever the beta function of each of the gauge nodes is 0, and in this n equals 2 4D situation, the beta function is proportional, say for this one, to twice the number of colors minus the number of layers. There is a formula like that. This is a one loop exact result, and so is 2 and 1 equals n2 plus f1 for the first, 2 and 2 equals n1 plus n3 plus f2, and so you have a set of equalities that you need to satisfy if you want this theory to be conformal. We okay up to here? Yeah? So what we have then to make it more clear is a situation like this. This is the type of field theories. Okay? This you may consider is not the most natural thing that may come to your mind, but okay, let's go with this. So this type of field theory is satisfying this type of relation. Okay? There is a way of encoding all these relations and all these numbers in the field theories in one function, and that way of encoding is super useful in holography. Let me tell you how that goes. So what I'm going to tell you is for a field theory with P nodes, one can define a function. People refer to it as rank function. It's a polygonal, convex polygonal function. So you see it's made out of straight lines. At x equals 0 is 0. At x equals p plus 1 is 0. That you read from there and from there. At x equals 1 is n1. At x equals 2 is n2. At x equals 3 and 3. So capturing all these numbers, that one, up to there. Okay? So that function captures those numbers. If you take the first derivative, you get a discontinuous, piecewise continuous function. If you take the second derivative, you get a set of deltas, and the coefficient of the delta functions are precisely what we were calling the flavors nodes before. So you see, for example, f1 is 2 and 1 minus n2, and that's precisely the coefficient you get of the first delta function, etc., for all the others. Right? So this is a function that captures, if you want, the kinematic information of this field theory. Okay? So I would like you to keep in mind this rank function. We are going to use it in an interesting way in holography. Any question about this or comment? So don't let me be too cryptic. Keep me under, yeah, keep me under my.
So can we
Say, please, Dan.
So you haven't discussed here like the larger limit function, whether
The larger limit will come. For now, this is NEN, NEF, satisfying this relation. That's what's important. The larger limit, and even more, the large quiver limit. This is where we pay the price. Actually, comes in holography. Okay. All right. So okay, there is this rank function. Let's keep it in mind. There is this. Now let me discuss the holographic description of this particular field. In 2005, there was a first attempt by Lin, Lunin, and Maldacena. This attempt was completed in 2010 by Gayotto and Maldacena. 2A version of this holographic duas is the following. SU2 and the U1 isometers. Those are must be. There are two directions that are free there, and I'm calling them sigma and eta. There could be Ramon and Neves-Schwarz fields. This is the most generic set of Ramon and Neves-Schwarz fields that you could have in this situation. And you see they have to live respecting the isometries of this background. So they have to live either completely inside the sphere, or completely in the circle, or in the sphere and the circle. And notice that there are functions, f1, f2, etc., up to f8. They can depend on these two coordinates. Any other dependence will break the isometries one would like to keep, and is forbidden. Okay? So, in principle, you have a background that could be the dual to these field theories we were talking before, but we want to impose supersymmetry on this background, basically what Elias was commenting. The way to do it is to write VPS equations associated with this system. These VPS equations are A, because they are functions f1 up to f8, A, partial, because the things depend on two coordinates, partial, nonlinear, and coupled differential equations. Okay, so it's in principle a very complicated problem to solve, but it happens, and this is kind of a nice miracle in all these setups, in the different dimensions, that if you start operating with these partial differential equations, you are able to solve all of the equations in terms of one function, or all of the functions in terms of one function. We are referring to it as potential, you will see why, and its derivatives. Okay? So for example, this function f1 is some derivatives of this potential divided some other derivatives, dot and prime are sigma or eta derivatives. So like this, there is an expression for all of these functions in terms of a single function and its derivatives. What's interesting in this situation is that this single potential function solves a very nice partial linear differential equation written there. Okay? So it's a Laplace-like equation. It needs to have some boundary conditions to ensure non-singularities of the solutions and good behaviors. And the most interesting thing is that the rank function of the field theory you are talking about acts as an initial condition to the problem. Okay? So the way the field theory tells the supergravity background, I want you to be the dual of me, is via this rank function. Okay? So let me tell you very briefly. If we have half hour, we sit down, we solve by separation of variables this equation. The solution will be this one. So it's a Fourier Bessel series, where the coefficients of the series are the Fourier transform of the rank function.
What is capital P?
Capital P is the length of the quiver. So let me go and to say better this thing to Elise. For a quiver of P nodes, okay, where the numbers are one up to and satisfying these relations, encoded all of them in a rank function like this, yeah, you basically write the holographic dual in this way. You write this potential, where that coefficient is that Fourier transform. Okay? And okay, this potential will solve this equation. With that potential, you write these functions f1, f2, up to f8. You put them here, that's the holographic. Okay? This is the way this is constructed. And the comment that Yanis was making, basically, where is the large n limit here, is that these backgrounds are trustable if the numbers p and each one of the n's are large numbers. Okay? So the most natural idea one would have is to do the theory that was kind of the darling of the 1990s, SUN with 2n flavors. Okay? In that case, the number p is not large, so that is not trustable. You will find singularities somewhere. You will find singularities that basically cover your whole space. Please.
What do you mean they are large? How do you, why,
Yes,
some
yes.
fluctuation, how
Very
do
good, very
you
good.
understand
In this way,
the
in this way, in this way. Very good, very good, in this way. These theories will have flavors. Okay? The flavors are represented by the presence of flavor breaks. So there are sources. The Bianchi identities are satisfied everywhere except in the places where the brains are. Okay? And this is basically encoded in P. Okay? The delta functions appear in the Bianchi identities So when you go close to that point of the space, you will find a singularity corresponding, in this case, in this particular case, to the singularity you find close to a D6 prime. Okay? So then you ask, I want the background to be trustable mostly everywhere. And then you say, you look at the dilaton, you look at the Ricci scalar, and you notice that 1 over B and 1 over N suppress the divergences. Okay? So you take them as large as you wish to make the background more trustable everywhere. Okay? And only in the position of the flavors you cannot trust. Is this answer? Yeah? Any other question or comment? Please, yes.
Instead of this type of piecewise continuous function, suppose I take a completely smooth function and pass through state point. What happens?
Very good, very good. So let me repeat the question of Elias because it's very nice. Suppose that instead of doing this, I take x squared, right? So minus x squared, function like this, right? So you can solve, it's a solution. The problem there is that the flavor groups are like completely similar, okay? So you lose a bit this picture. Okay? You lose the picture of I have this color group and I have this flavor group, right? So that's the thing you pay in that case.
Is that corresponding to fixing of this group?
I would say no. Fixing is another thing in this context. Okay? Fixing is another thing. Very good, very good. I think this is the price we were paying in the early mid-2000s by smearing the brains, right? Yeah. It was a different smearing, but it would be akin to this. Okay? Very good, very good. Very good. So the algorithm I want you to keep in mind is the following. Think about gauge theory, right? Make sure to be conformal that it satisfies those equalities. Write the rank function. Write the function B. Write the function Z1 to F2. Put it here. That's your holographic dual. Keep that in mind. And another thing I would like you to keep in mind is that somewhat the geometry of the holographic dual is encoding the field theory in this direction eta, because it's the direction I'm using to label the rank function and use it as initial condition. So there is one direction in the holographic dual, this one, that I will refer to it as field theory direction. This will come towards the end of the talk, this kind of interpretation. So just to say briefly, many checks in supergravity and in field theory of the equivalence between these holographic duals and the field theory. Most of these tests rely on calculations, either on the holographic side, on string theory, or in field theory, localization and matrix model calculations. Okay? And these things work in all the different dimensions, 1, 2, 3, 4, 5, and 6, where superconformal theories. Okay? So there is this picture. Please keep in mind the quiver direction is somewhat this eta direction. Okay? So this is about the conformal theories. What I will spend some time now is leaving the conformal point and moving into a confining or gap theory. Okay? So any question or comment, and then I'll move it to that. Please.
You mentioned these colors, but always the sigma is applied in the string or
You may think in this case, eta goes from 0 to p plus 1, so it's an interval. Sigma goes from 0 to infinity in this particular case.
in the larger universe.
Yeah, it becomes large, but finitely large, right? So it's p. It's a number that you control. Okay. The other is infinite. All right. So let's keep in our minds these conformal field theories. They will act as our UV fixed points from which we will make a Wilsonian deformation. The idea will be the one we discussed before: high energies having a CFT4 in the case we are discussing, deformed by BEVs or inserting relevant operators. There is a flow typically into some infrared dynamics, typically strongly timed. On the holographic side, we will take this ADS5 times M5 backgrounds that we had before, with some Ramon fields that we had, what will occur is that we will switch on different components of the Raman fields and we will change things in the metric. There will be a flow in the geometry that will lead to some infrared geometry, trustable, and we will use it to learn about this. Okay, that's the goal.
Sorry, Carl.
Please.
What this solution is not a conversion to magnetic field, right? The inner space, let's say, is not compact. Is that correct?
No, it happens. Very good. So the question that Elias is asking is these two directions, eta going from 0 to p plus 1 and sigma going to infinity, looks like a non-compact space. When you calculate the volume of that space, because of the fact that Bessel functions appear, this volume converges. Yeah. So it gives you a finite value. This is one-to-one related with the fact that the central charge of this field theories is finite and a given number. Okay? So it might look infinite, but when calculating it's finite, actually, because of the Bessel killing the
So
infinity.
that means we can put another coordinate where it looks fine.
Yeah, of course. Only that in this coordinate looks particularly nice. And many things become super nice in this coordinate. All right, so this is the formations we are going to discuss. We are going to consider some ADS phi times M phi manifold. This is the ADS phi in the same coordinates that Kostas used earlier today. And in the M phi, I'm going to separate a U1. Okay? The formation will be the following. Take a circle in the directions of the field theory and put some function of the radial coordinate that you also have to put here, making these two directions a cigar-like direction. So these functions are known. And also at the same time, fiber mix this U1 of the internal space with that direction. This is this twisting I was referring before. This type of metrics are known since before 2021, but they were put back into the game in a paper by Andrés Anabalón and Simon Ross. Then this type of compactifications very nicely studied by Prem Kumar and Ricardo Stuardo in 2024, and also in 2022, things are different picture. Kasani and Komargovsky studied this type of compactifications where a CFT4 is compactified to a quantum field theory three-dimensional times a circle, and this circle is twisted with the RC. Okay? So in ADS terms, what one is doing is exactly this thing here, starting from some ADS, putting a function that is basically deforming the isometries of ADS, breaking them, and mixing this R symmetry with this direction on the field theory. Holographically, what we will have, as I will show in a second, is three dimensions, a cigar-like two space, mixing with a U1 of the field theory. So what I'll show you in the next slide is purely technical. There is no need to understand anything there, but let me show you just to tell you that the thing exists. That is going to be this type of patterns. Let me just say once again, coming back here, what are we doing field theoretically? You have a UV conformal theory with an R symmetry. You pick a U1 of that R symmetry and mix it with the circle direction of which you compactify the conformal field theory. The whole background is moved. Thanks to this mixing, this twisting, one preserves some amount of supersymmetry. This makes the resolution of the equations of motion and everything nicer and simpler and ensures stability. The gravity indicates a transition from a CFT4 to a quantum field theory in 3D that is gapped with a smooth infrared. And one can play this trick that I mentioned. This goes for the thing that Elias was asking in the beginning, in different scenarios. For example, in the CFT4s that we are discussing before, but also in any other direction. So what I will show in the next slide is the metric. There are accompanying Ramon and Levy-Schwartz fields that I will not display, but they are in the papers. That are the holographic description of this conformal field theories deformed by a verb leading to a gap system. Okay, so that is this. Okay, so just for you to read it a bit, without entering importantly, that the field theory is somewhat anisotropic in the following sense. You are having here a dual to something that is a 3D quantum field theory, gap and nice in the infrared, strongly coupled. But as you pump up the energy, you grow a direction and you end up in a 4D conformal field, right? So the system is anisotropic. And that anisotropy is revealed there, if you wish. Also, there is a web for a current that is represented by a parameter. You can calculate different things. Let me tell you one that I like and is visual. In this type of anisotropic backgrounds, one can write something that is a generalization of the Brown-Renaud formula, the central charge. Okay? So it's a Nagy formula I'm writing here. Let's not stop in this. Let's just say that this just generalizes the Brown-Renaud formula such that if you evaluate it in ADS backgrounds, it gives you the same result as Brown-Renaud. Okay? So you can take this background that I'm writing here and go over all the exercise and write this flow central charge and write it and write the flow central charge divided by the central charge of the UV conformal field. If you get something like this, where F is this function deforming the background that we had before. When you plot it, you find something that goes from 0 to 1 in this case. And so what this is telling you is that you have a system or you have a quantity that is interpolating between the UV CFT in 4D and the 0 degrees of freedom of the gap field theory. Okay? So what's kind of nice about this is that this is a flow across dimensions. So there seems to be, at least holographically, a quantity that detects this flow across dimensions in a monotonic way. So this is kind of a nice problem for field theory. Notice it, anisotropic field theory, going from 3 to 4 dimensions. Can one write a quantity that is monotonic, going to the AR, and basically can be associated with the number of degrees of freedom? At least holographically, one has this type of case. And there is something else about these quantities. Let me say this briefly because the time is short. There is the following way of thinking about this. If you move this to the multiplying here, what you can see is that this observable sort of breaks into 2 bits. One bit that is the corresponding to the UV conformal, and one bit that is corresponding to the flow. This breaking of observables into something conformal and something related to the flow is something that happens to many other quantities. And actually, I think it could be thought as a consequence of a very nice development by Gaudet and Varela in 2007. Some theorem on compactifications they made, some conjecture on compactifications they made in 2007. Let me just say that this breaking is very non-trivial for a field theory viewpoint. So let me, in the last 5 minutes, let me comment on something that is very not universal and follows from a question that Kostas Petsos asked in February of this year. Before I go into that, any question or comment?
Sorry, Carlos, I think I missed it. What is the seed flow that you, three-dimensional, what does it correspond to field theory?
So what this seems to be indicating is you have a field theory that in the far infrared has no degrees of freedom, 0 degrees of freedom. As you start pumping the energy, something happens to the field theory that goes to the number of degrees of freedom of a 4D conformal field.
Yeah, but is there some intrinsic definition of DC flow for
question that Kostas was asking was, what happens if you calculate the Wilson loop here? Is the Wilson loop stable under fluctuations in some of these extra directions of the hologram? So this leads to this part of screening. So we have a system where we have color groups and flavor groups. Okay, so it's natural to wonder, can we have some form of screening here? Could the Wilson loop be screened? So to address this, we consider string probe that moves typical calculation of Wilson loops, moving X, moves in time, explore the radial direction, but also has the possibility of exploring the eta direction. Okay, so the quiver direction. And okay, this leads to a complicated Nambu-Goto action that leads to complicated Euler-Lagrange equations. And in work with Ali Fatemi-Bari and Mauro Filiberti, this Mauro is very specialist in numerical problems, and he devised a way of solving this problem by just doing a minimization of the action that basically search for the minimal solution. What we find, and this is the bottom line, and I will show you plots in what follows, is that the probe fundamental string not only moves in the radial direction as the usual Wilson loop, but also wants to go search for the flavor groups. Okay? So there is a form of screening here that is very non-universal because it depends on which quiver one is thinking. And so let me briefly comment on this screen and then show some plots. So the type of screening we are seeing here is very different from the one in chromodynamics, in the sense that in chromodynamics we introduce a very heavy Wilson non-dynamical quark-antiquark pair. We start separating them, a flux tube forms, and at some point it's better, rather than keep stretching the flux tube, to create a quark-antiquark pair, dynamical quark-antiquark pair, and then two mesons fly back. In here, something else seems to be happening. Suppose that we calculate the Wilson loop here. It seems, from the plots I'm going to show you, that an operator is created that starts exploring the quiver up to it can reach to the flavor group, make the screening, and then separate without further energy expense. Let me show you this in plots. So these are numerical simulations. Take that quiver, write the holographic dual, calculate the Wilson loop with this Nambu-Goto action. Right? So this is what it is, and this is what you learn. All these plots, these are for different lengths of the quiver. All these plots, they have a region that is conformal. That's okay, because at very small separations you are exploring the EV. That's conformal. There is a region that is linear behavior, so confined in light, but then it flattens. Okay, so and what you can see is that the conformal, the confining bit is the longer the quiver is. So it takes more and more energy if the flavor group is very far away. It takes more and more energy to pair produce. Okay, you have to explore the whole quiver. And this is a plot of the, as you stretch the strings, how they penetrate into the bulk and how they try to go into the flavor.
Carlos, what's the mass of the core?
Zero in principle. But you have to produce it. You have to go there and produce it. That's what spends the energy. Okay? So suppose we start in this color group, there is no flavor around, but there is one over there. So I first have to go there, pair produce it, and that's what takes this energy.
If you start there, shouldn't it be?
Yeah, it takes nothing. Yeah, exactly. Look, this is the opposite of that. What I'm showing now is the opposite of that. You can take a symmetric quiver and start on this side of the quiver. So what you see in that case is that the strings want to dive into this flavor group. Or you can start on that side of the quiver and see that the strings want to dive onto that. But if you start in the middle, the string doesn't know where to go. So even when there are flavors, seeing some form of confinement. Okay? All right. So all these numerical experiments, we are able to concentrate in one very simple formula for the energy of the quark-antiquark pair in terms of the separation of the quark-antiquark pair, in terms of three parameters, A, gamma, and B. And this formula is nice enough that, and by the way, is fit by all the numerical experiments with a high precision. So the formula is nice enough that for short separation, it gives you a conformal bit and a confining bit, and for long separations gives you a screen like this. Okay? There is probably a lot of physics hidden in these coefficients and how they depend or not on the quiver, on the numbers N1 and 2, etc. Let me, because the time is done, let me just conclusions, and that's it. I have presented some D equals 4 generic formalism to right string duals to conformal theories. This is valid in all the possible dimensions with a Poincare supersymmetry. I have focused on the 4 details. I have shown how to use these conformal theories as ubiquitous points for an Archie flow, ending into a gap field theory. It's possible also to find solutions that end into another fixed point. There are various observables that are interesting to study. Some are universal, some are not. It's interesting to better understand how the dynamics is influenced by this flavor degrees of freedom. And I'm presently exploring these kind of situations in different situations with or without subsets. Thanks very much. Sorry for the
Thanks, Carlos, for the very interesting and clear talk. Do we have more questions?
Can I go back to the C function that you had? So the 4D denominator, was it the C anomaly or the A anomaly?
A. So, okay, the holographic C is equal A, as you showed, right?
Oh, there you go.
Right? So in that case, in this large chain, etc., A is C, right?
Yeah, so it's still
But it's
possible.
A. It's A.
But how do you know?
How do I know it's A and not C?
Yes.
Yeah, I
Because
don't know.
the C would appear the two-point function of the n-geometric vector, and that would commute along the floor.
But I think I could just continue, right? And then
Okay, the only thing that makes me doubt is because of the breaking of Lorentz in here, right? But holographically it can be calculated,
Yeah.
right? Because it's just looking at the metrics and
going to go through the problem of turbulence, and maybe towards the end I will present a small model that we have recently found. Okay, before I continue, let me mention these things. This talk will present a personal view of what the turbulence problem is. If there was somebody else here might have given a different talk. I will try to present the challenges and where we are right now. And it will not be in historical order, and we'll mention some stuff along the way, and they're not going to be in historical order, do not confuse yourself. I will shove a lot of important issues under the carpet and pretend they don't exist. It's the only way I could move forward and complete this in 45 minutes. And I will not do justice to many researchers that have worked in the field, and I won't be mentioning, and they should have been mentioned in a talk about turbulence in general. Okay, for the last two, I deeply apologize. So let's begin. Why study turbulence? That's an easy question to answer. It appears almost everywhere in the universe, in interstellar medium, in galaxies, when we are swimming, when we are driving our car. Turbulence is everywhere, and it spans a huge number of scales with great applications. So I have a list here of different scales that one meets turbulence, from galaxies, interstellar medium, solar wind, the sun in turbulent convection, the atmosphere, perhaps the most important role of turbulence is in the atmosphere. It affects our life daily, in the ocean, in ships, in airplanes, up to our coffee cup when we pour milk in it. So it covers a huge amount of scales. Let me tell you why it is important. Okay, it's there, but why do we need to take it into account? So this is an example. Suppose you drive your car with 72 miles and kilometers per hour. 72 because it divides easily by 60 and 60, so that's 20 meters per second. Okay? You drive through the air, and you want to know how much energy you dissipating due to the movement of the air. So fluid dynamics tell you at the rate that you dissipate energy is proportional to the viscosity of the air times the density times the integral of the gradients of the velocity around the car that is moving, the part of the air that is moving. So we have 72 miles per hour. That's a typical velocity. You have a typical size of a car around 2 meters. You can plug in, you know the value of the viscosity. You can plug things in, and estimating the gradients as velocity divided by length scale, you will get a value of rate of dissipation that is tiny. It's very small. What happens is, in reality, is that there is turbulence, and that estimate of the velocity, gravity, and velocity divided by length scale is very wrong. What turbulence will do is move that energy to very small scales so that it's dissipating much more efficiently. And that will give an estimate that is independent of the viscosity. That's a very well-known fact for turbulence. So if you estimate the rate of dissipation of energy given that low, one gets a much higher value. What is U? U is the typical velocity of the car. Okay? So if I take the product, the ratio of the two dissipation rates, I get a number that Newton's law is. Newton's law for a continuous medium that we're dealing with here, and we're still talking about it. The second quote is from Heidelberg. Sometimes it's also attributed to Horace Lamb, fluid analysis from Cambridge. I kept Heidelberg because many of you don't know that his PhD was in turbulence under Sommerfeld. And let me quote, can't really forget my glasses today. When I meet God, and I'm going to ask him two questions. Why relativity and why turbulence? I really believe he will have an answer for the first. And the last quote is from the fluid analysis from Caltech that says, turbulence is a graveyard of theories. Been around a very long time, and people have failed to have a complete theory around it. Okay. With these quotes, let's move. What are we looking at? So we are, the equations that we are solving are known for a very long time, named after a French engineer, Navier, and a British mathematician, Stokes. The Navier-Stokes equations were, this is the time derivative of the velocity. We have a nonlinear term, the advection plus the pressure. Viscosity that is responsible for dissipating the energy, and in general we also consider a force that injects energy to the system. Okay, looks very simple, and you can put them on a t-shirt. Yes, we still have
That's uncompressible fluid.
incompressible. I'm talking about incompressible. Throughout my talk I will be considering incompressible fluid. Okay, let me mention three problems that appear from this equation. One, it's nonlinear. It's nonlinear, it implies that we have chaos. We are no longer talking about trying to find exact solutions to the Navier-Stokes. We want the statistical behavior of the solution to the Navier-Stokes equation. Okay, so that's one problem. The second is that we are non-local in space. What does that mean? In order to find the pressure that I put there, you need to take the divergence of the equation, then you end up with this equation over here for the pressure. That you need to invert a Laplacian. Invert a Laplacian means you need information about the whole space. So there is an eddy at the end of the room. I can fit it here in infinite time, in zero time. Okay? Of course, we hope that the eddy up there is not as much affecting as an eddy next to me, so we can do some assumptions that only the nearby eddy is affected, but that we need to keep in mind that it's not exactly true. Another problem that we have is due to nonlinearity, it's non-local in scale space. So old scales coupled with old scale. Okay? So keep these things, three things in mind, because we're going to look them as we move on. Okay. Being
This equation, this last one, what have you done? So you make some Fourier, like...
I Fourier transform the equation. So I write the velocity field in terms of the Fourier transform, plug it in, and that's what comes out. Okay? Being hard to solve doesn't stop us from doing experiments. So this is some of the state-of-the-art today of what we're doing. We want the large Reynolds number, which is U times L divided by viscosity. So we want as much higher velocity as we can. And then if we want it larger, there are two ways we can do. Either increase the size of the domain. So that's what is done in the first picture. This is an air tower in Lynn. So we make it as big as we can. And nowadays, it's the size of buildings, not just rooms, buildings. Oh, you see there is 150 meters long and 40 there. The other direction we can go is decrease viscosity. And a nice way we can do that is to take liquid helium and go the record today, and it's been done the last year. The publication is not appeared yet. So this is a simulation in 32,000 grid points in each direction. About 32,000 to the cube, 10 to the 12, 35 times 10 to the 12, 10 to the 13. That's a huge, huge size of simulation that I don't know how many CPUs how many millions of CPUs we use to get. But nonetheless, it can be done. It's expensive, but it can be done. And the good thing is that we get information about the whole domain, not just where we have put our probe to measure things. We know everything about the whole domain. Yes?
I thought that the PDFs are not well housed. How did they do this?
What?
I thought the PDFs are not well housed in the long term of the day, just for short periods. How did they do this?
They are well posed. I don't know what it means if they're not well posed.
An initialized problem.
Oh, you're talking about the singularity problem.
Yeah.
Well, this is done on a finite grid. The method they use is what they call pseudo-spectral methods, so that means they solve it in Fourier space, and they keep a finite number of modes.
Let me ask the opposite question. In fact, this includes a lot of numerical viscosity. So
No.
how do you get that?
No, if you do it well, you don't have numerical viscosity. If you do it well, or at least
People
in a
that I
controllable
talk to,
way. If you do it
saying that
well,
it's
you can
very
control the numerical errors that we have, and you know how much they are, and you can throw them away. You know if you can throw them away. With these guys, I think they did.
Numerical viscosity mean being not very good in numerically solving equations.
There is
I
an
don't
error when you solve
understand.
numerically some equation. There's always some
If
error.
you discretize, you don't have energy conservation.
Now, if you're doing a PDEs, you also want them to be stable. That so it doesn't blow up with high frequencies appearing. So that usually people add something that dissipates very high
But
wave
then
mode.
people take the continuum limit, I assume.
Well, they're trying to simulate the continuum.
Because that's a tricky limit to take in lattice theory, for instance.
Yeah, but what we do want to simulate is the continuum. We don't want to simulate the discrete. So people try to do the best they can to do that. Let me move to the next slide and I'll explain it better. Okay, you all do that experiment. We all do that. Under experimental simulations, we get energy spectra that look like that. Energy spectra means energy per unit wave number. So how much energy you have at this wave number, how much energy you have. And in general, you get a plot like that. You force here, there's a power law decay, and then it drops where the dissipation is effective and it starts to dissipate. Okay. Now simulations, last of the question before, if we need to believe them that they simulate correctly the continuous limit, they should have a grid that is much smaller than this exponential that you drop. And then you kind of know that the error you're making is dropping off exponentially the smaller the grid size. There will always be an error. I mean, otherwise, we would be talking about exact solutions. There will always be an error, but we can control it on how fine grid we have. Okay, so this is what we will be trying to describe. But let me put the question, what is turbulence? And it's, in general, if you go to books on turbulence, know how to solve that. And for example, we meet that when we simulate the gas in this room. Huge number of degrees of freedom. There is also a usual condition. We can write down a PDF for the position and velocities of the molecules in this room. And take some form like that depending on the particular dynamic. Okay, so that's what we call the canonical ensemble theory. And based on that, we can derive anything that we want. Relation between pressure and density and temperature. So we want something like that for turbulence as well. Equilibrium dynamics, as done here, have been tried in turbulence. And the first time they were done by these two guys. The top guy is TDV. We did the microcanonical ensemble for an ensemble of Fourier modes, of velocity Fourier modes, and predicted an energy spectrum that was like k squared. That's his only paper on turbulence. Then he left and went to win a Nobel Prize for weak interaction. The second guy is Robert Krajnat, who was one of the last assistants of Albert Einstein. He did what is called in statistical physics the canonical ensemble. He also finds k to the square. He never left the field of turbulence, and he only won a direct Dirac medal. Okay. So k squared does not look what I showed you before. What I showed you before was something decaying power law. But however, for scales above the forcing, when there is no flux of energy, they do seem to give a good description. And in fact, our group has done lots of simulations for these scales, and indeed they form a spectrum that looks like a square. And it does also obey some fluctuation. The interesting part here has been tried to be solved by many researchers. One of which is this guy. What? It's in a log-log scale. Everything is in log-log scale in turbulence. So one of these guys is this guy, which I'm being quite unfair only mentioning him, but I got my PhD in the University of Chicago and I'm a bit biased. And second, it increases the number of Nobel Prize physicists that worked on turbulence by one in my talk, so I put him there. I'm sorry for all the rest. And they were trying to describe the statistical behavior of eddies of different sizes. In particular here, they were trying to model the moments of velocity differences. So you take 2 points, measure the velocity here, measure the velocity here, find the difference, and then raise it to some power and try to find the equation for these moments, which leads to a hierarchy problem. So to get the second moment, you need the third. To get the third, you need the fourth, and so on and so forth. So in the end, it didn't lead anywhere. The guy that really pushed the field forward is this Russian mathematician, Andrei Kolmogorov. Now what Kolmogorov said in loose terms is consider an ensemble of turbulent eddies. These eddies, what they do is transfer the energy from large to small. Energy is conserved. So this flux of energy from large to small has to be constant across scale. Otherwise, you won't be preserving energy. And then if you do an order of magnitude estimate, the flux of that energy should be proportional to the energy you have at a given scale times the rate that you move it down, the time divided by the time scale that you move it to the smaller scales. And that time scale should be of the order of the turnover time, so L over U. And you plug it in, you get this relation. Q cubed divided by L should be proportional to the flux of energy across scale. And that should be equal to the rate that you finally dissipate energy at small scales, or to the rate that you inject energy at the top. Okay, so we get a relation between the velocity and the scale, but this is a constant. So the velocity scales like L to the 1/3. Okay, and now if you plug that in to the energy spectrum is energy divided by wave number, per unit wave number. So that should be U squared divided by K. K is 1 over L. You plug it in, you end up with a spectrum that is K to the -5/3. That's a famous Kolmogorov spectrum. And it has met a huge success. The Kolmogorov spectrum has been found in many, many different situations. I put three figures here. One is from engineering flows, pipe flows, flows behind grids, flows behind objects. And they found this case in the minus 5/3. Second is the atmosphere. People measure the energy spectrum of the atmosphere. They're finding green 5/3. And the last is from interstellar medium. That they also can fit the data in the power law and give us also the case of the minus 5/3. Expression at third is that the Kolmogorov's fingerprints are all over the universe. Spectrum k to the minus 5/3, that's 1.666. If that was true, we would be done. If that was true, the only thing we would have to calculate is the prefactor in front of that spectrum, and we will know everything. If that was true. However, it's not true. If you do more precise measurement, you find it slightly steeper. Not a lot, but it's slightly steeper. It's bizarre, and it's around 1.76666, so around 0.1 correction.
Still
So,
universal. Still universal.
Still universal, as far as we know, because there are not that many measurements that can measure this with this precision. We hope it's universal. Let's say that. Okay?
Of the pool we had before, right? That it was like this with the pump and then
Yeah.
and this is this last part. Yeah, how many decades is this?
So
Okay.
that's that part. The
Yeah.
one for it has some blue arrows pointing boom, boom, boom.
Yeah. How many decades?
How many decades of what?
Well,
In
I mean,
which
in the
case?
scale, how many? The 10 to the third? How many?
So here it's 1, 2, 3, 4. Here it should be even more.
And the 1.76.
The 1.7 is how many scales do you need? I got that 1.76 from something that had something around 2. It was from a numerical simulation. The problem with the cases like the atmosphere, that is not so well controlled. So
And the end of that behavior, what sensor?
the end of that behavior, that's viscosity. So up to here, energy is conserved. Then viscosity starts to become effective because we are very small scales, and the anticipation for photons of the gradient of the flow, and it drops exponentially.
But the arrow bar.
It depends on the case. It's not my data. I cannot really comment on
I'm
that.
very surprised that from 2 decades you can tell the difference between 1.66
Yeah,
and 1.7.
that's why I'm asking.
It's around there. Okay, maybe it's overestimated or it's underestimated, but it's not my measurement, and I'm not here to talk about that. Okay, so let me explain what's going on. Kolmogorov was a mathematician. He did not present what I showed you before. What Kolmogorov could prove, and that's a theorem, is that this relation holds. That the third moment of the parallel velocity difference, so that means you take a point here, you take a point here, you project the velocity along this direction, and you find the difference and raise it to the third power, is proportional to minus 4/3 times epsilon times r. That's a theorem. That you can neglect forcing and viscosity, that should hold. Okay?
R is the distance.
R is the distance between the two poles. Average over all possible positions. It assumes isotropy and homogeneity. I should say that. So that is something that is mathematically true. What Kolmogorov did say that since the equations of fluid dynamics and Navier-Stokes are scaling variant, they're non-linear factors. So if we assume that the solution is also scaling variant, then the moments if you raise them to the rounded power, so it's delta u to the p raised square divided by delta u to the 2 raised to the p, that should be something that should not depend on the scale. So if that's true, then the moment should scale like that. So he could prove the case of p equal 3, the case of p equal 2 should be that, so that will be r to the 2/3. R to the 2/3, if you translate it to a spectrum, because the second moment is related to the spectrum, that leads to k to the minus 5/3 with this CP being universal. Okay, that was the original theory of Kolmogorov in 1941. It's met many objections despite the verification of lots of experiments, mostly by this guy. That's another Nobel Prize physicist that worked on fluid dynamics, which is not surprising because Landau worked on everything. And the argument of Landau is that, okay, if these are all these CPs are universal, and it holds for one flow, if you consider a super ensemble of flows, then the same thing should hold, and that should lead, if CPs are the same for this super ensemble, to this relation here, which is true always if P is equal to 3, because the two are the same, and it's also true if epsilon is the same, so this super ensemble then injection is the same for everything. But if there are variations, this cannot be true. So the Kolmogorov minus 5/3, although it has received this huge amount of verification and strong empirical validation, it's not mathematically exact. There is some correction, and it lies to the fact that we assumed that there is scaling value. So that forced Kolmogorov 20 years later, 21 years later, to revise his theory and say that still power loss, but not necessarily linearly related. So there are small corrections. Corrections, however, that could not calculate. And the plots here, it's the PDFs of velocity differences at different scales. And the PDFs change as we change scales. So that means that they are not so similar. This is clear. If you are at some scale, you can look at the PDF of the velocity difference, and you can tell at which scale you are. Okay, because the PDFs are different. And this is the measured exponents from, I think it's from numerical experiments. The straight line is what Kolmogorov K41 would predict, and they clearly bend. This is particularly if you look at higher moments, they are not linearly related. So self-similarity is broken. In the next slides, I will try to convince you that this is something that maybe we should have anticipated. Of course, it's easy to say that after you know the result. Anyway, I'm going to do it. So I would like you to consider a structure like this. So these blue circles here represent eddies, and as you move up, you move to larger scales, and as you move down, you move to smaller scales, and you populate with more and more eddies as you go down. Okay? Because smaller eddies, if we can fit more smaller eddies in the same block. Okay, so the idea is that you start one big eddy, it gives its energy to two smaller eddies, those two smaller eddies give the energy to the two smaller eddies, and so on and so forth, until you reach viscous dominated size eddy. Okay. So, and you do that at the rate that, as Kolmogorov predicted, is proportional to 1 over the turnover time and so on. Okay, then if we look at an eddy down here, and we want to know what is its amplitude, well, you know the amplitude of this guy, so times R, which is the fraction of the energy that it gives to the one guy, because you don't necessarily assume that they give the same amount in both cases. Suppose it's a random process that at every step we decide to give this part, this eddy, this part, this eddy. So it will be this times R2 times R3 times so on and so forth. So the eddy down here will be the product of all these R's. It will be the initial energy up here times R1 times R2 times R3. So it's a product of random numbers. And this product of random numbers makes the whole difference. So if it was 1/2, then we completely represent regarding the Kolmogorov scale. If, however, it's random, we will end up in something that we call multifractal scaling or harmonious exponent, and I will explain a little bit why we call this multifractal. If you go to step 2, when you have 4 eddies, and if, for example, the 3 of them get equal energy, and the 4th one is absent, and then we repeat that every 2 steps, so we have 3, and we move 1, then that will converge to a fractal set. Now, if you do something a little bit more complex, every 3 steps you remove 3 and you keep 5, and then you repeat that, you get another fractal set that is dimension log 5 over log 8, and so on. So if you do it randomly, in principle, you have all this fractal structure, and that gives something that we call multifractal scale. Okay? But let me tell you why this random product of random numbers is very different than one would see. What did I do?
No, it's just to remove this from the screen so that you can see your typing.
How much time do I have?
About 10 minutes.
About 10 minutes. Okay, maybe I should have it.
12 minutes.
Okay, so let's consider these 2 gambling games. It's the time of the season when people start gambling, so suppose we are flipping coins, and there are 2 betting strategies. In one case, we put €1 every time, and in the other case, we bet half of our money no matter what we have. Okay? So in the first case, if you win 20 consecutive times right from the beginning, if you start with €1, you will end up with €21, which is very good. In the second case, if you do the same, you will end up with €3,300, which is even better. So the 2 events have the same probability, they didn't change anything with the coins, but in the one case, we can reach much easier, more extreme events. Okay, so the first case is very well known. This is a random walk. So, well, more precisely, it follows a binomial distribution. You can write the binomial distribution in terms of gamma functions, use the Stirling approximation, and you can get a PDF that looks like that. And if you expand around y equals 0, you will get a Gaussian. And you can calculate all the moments with this Gaussian, and then form a relation like that, which is kind of the relation that Soboborov used in 41 to predict the KT minus 5/3. Let's do the same thing for the other game. So this is not a sum of random numbers. It's a product of random numbers. But if you look at the log of the money you have, it's a sum of the log of random numbers. It's also random numbers. Okay, so we can do the same thing. There is some